Okay. Yeah. Good evening to everyone. Hope you are fine. And welcome to this session. So yesterday we have started the two alternates in parallel. Okay. Two alternates in parallel for two cases: effect of change in excitation and effect of change in mechanical power input. Because alternator, it can be controlled only from input side. There are two inputs are there, na? Two inputs. Controlling is from input. One is excitation, another one is mechanical power input. And two cases we have seen: effect of change in excitation, effect of change in mechanical power input. So for change in excitation, when two alternates are connected in parallel, if excitation of any one machine is increases, the set terminal voltage will increase and vice versa. Set terminal voltage increase, vice versa. Increases, decreases. But to maintain the same terminal voltage, what to do? Decrease the excitation of other machine. And when excitation increases, synchronizing power, the synchronizing power will come into picture, which is the reactive power. For changing excitation, synchronizing power is the reactive power. It demagnetizes the one machine and magnetizes the other machine to maintain the terminal voltage constant. Okay, yes. And yeah, similarly, for effect of change in mechanical power input, we have seen the mechanical power input. So when mechanical power input of any one machine increases, its angle delta will comes into picture, that will causes the resultant voltage between E1 and E2. So that will drive the current. Right? Synchronizing power, but synchronizing current and synchronizing power is the active power. When prime mover input increases, active power. Okay, yeah. But if mechanical power input of any one machine increases, right? Set frequency will increase and vice versa. But to maintain the same frequency, if prime mover input of one machine is increased, frequency increase in to maintain the same frequency, decrease the mechanical power input of other machine. Okay, yeah. And even loaded condition also we have seen. Loaded condition also conclusions are same. And under loaded condition, effect of change in excitation, it will causes only change in its reactive power sharing. Because synchronizing power is reactive power, I have given the table. So when excitation changes, only there will be reactive power sharing changes. There will be no change in its active power sharing. No change in its active power sharing. And based on that, current changes, power factor changes that we have seen in both the cases. When mechanical power input changes, only active power input will be changes. Right? Yeah. Coming to, okay. Yeah. So last class, last problem. Solution not, I will do it. I will do it. Yeah. So before going to so we need to do the problem. Some of the students, so he asked a doubt, a query. So the yesterday problem is not uploaded. There was a big problem after the break, the network issue. So the reason I was trying, but so it was delayed. The class is also nearly some 10 minutes because of that. So today I just want to overview, and we will do some more problems also. Don't worry. Okay. And yesterday some students, they asked the doubts, and also they kept in the message asking the doubts. Just I want to clarify those things. Of course, others may be having the similar doubts, but anyhow, all the notes are there with you. So just listen. So wherever their doubts are there, so I just let us discuss, and then we will go to the problems. Okay. It's for some time. Maybe others also having similar doubts. Yeah. Mainly the doubt is, First one, effect of change in excitation. No? See here. Yeah. Case 1 I have taken. Case 1, effect of change in excitation. Quickly I will review. Effect of change in excitation. Under no load condition. No load condition. See. I was explained with the equation, but you cannot able to connect with that concept. Mainly, you should know the importance of that synchronizing power. So, let me discuss brief about that. Two alternators connected in parallel under no load condition. No? Yes. Yeah. This is ZS1, ZS2, E1, and this is E2. E2. This is terminal voltage V. Okay. See, initially their voltages are E1 and E2. This is E1 and this is E2. With respect to local circuit, I have taken both are in phase opposition with respect to local circuit. And when excitation of first machine is increased, initially I have started with 400 volts. This is also 400 volts. Then what is the terminal voltage? Also 400 volts. Terminal voltage is 400 volts. Fine? Yeah. And when excitation of machine 1 is increased, if excitation of machine 1 is increased, E1 will increase, na? Yes. If excitation of machine 1 increases, then E1 increases to E1 dash. E1 increases to E1 dash. Fine? Yeah. So that E1 increases to E1 dash means, let us take it is some 450 volts. I told it is around E1 increases to E1 dash. This is increases to E1 dash. That E1 dash is equal to 450 volts. Say E1 dash 450 volts has increased. Just I want to show with numericals because students are asked numerically how they are coming. Right? 450. Due to that, what happened? Synchronizing. This is E1 dash. Due to that, there is a resultant voltage. That is synchronizing voltage. That ESY is equal to E1 dash minus E2. Synchronizing voltage, na? Yes. Due to that, there will be synchronizing current ISY. So with respect to ISY, it lacks E1. Therefore, machine 1 operated ZPF lagging. Machine 1 ZPF lagging. Whereas machine 2 ZPF leading. Machine 2 ZPF leading. Correct? Yes. And synchronizing current will comes into picture. That is circulating synchronizing current ISY. It is delivered by the first machine, absorbed by the second machine. Absorbed by the second machine. Okay? Yeah. And even before, see, before increasing excitation, the terminal voltage, this is 400 means this is also 400, na? This is also 400 volts, 400 volts, terminal voltage 400, this is also 400 volts. Then terminal voltage is 400 volts. First, without changing excitation. But when excitation has changed, E1 increases to E1 dash. Let us take that E1 dash is equal to some 450 volts. 450 volts. That will drive the current. That will drive the synchronizing current ISY. Delivered by the first machine, absorbed by the second machine. That is the synchronizing current, synchronizing power. That synchronizing power is reactive power. Na? I was explained with the equation. It is a reactive power. Delivered by first machine, absorbed by the second machine. And the synchronizing current, synchronizing power, demagnetizing the first machine. It demagnetizes the first machine, magnetize the other machine. By demagnetizing, what will happen? Its voltage is not 450. First, soon after excitation increase 450, but due to demagnetization, it is some 430 volts, say 430 volts. And it is magnetizing second machine, its voltage also will increase. How much it is? Some 410 volts, say 410 volts. 410 volts. And then synchronizing current still exists. It is continuously exists. And this is 430. Some 10 volts drops in this. 10 volts drop. 10 volts drop in the synchronous impedance. IZS, no? Yes. Then 430 minus 10 is equal to how much? 420 volts. This is 420 means this is also 420 volts. 420 volts. Then what is the terminal voltage? Here also 10 volts drop. 420 means here also 10 volts drop. In this also 10 volts drop. Then what is this voltage? It is 410. 420 minus 410. But finally what happened? Set terminal voltage has increased. This has increased to 420 volts. 420 volts. That is what I have explained. And when excitation of any one machine increases, set terminal voltage will increase. Set terminal voltage will increase. And vice versa. If you decrease excitation, set terminal voltage also will increase. But to maintain the same terminal voltage, what to do? Decrease the excitation of other machine. That's what I was explaining. And same thing also, you can correlate with the V is equal to what I have given, E1 plus E2 divided by 2. This is the equation we have derived. E1 or E1 dash, whatever you say. Simply first machine voltage, second machine voltage. Now see here, when excitation of first machine increases, E1 increases. Definitely V1 also, V also increases. E1 increases, V also increases. But to maintain the same voltage, terminal voltage, what to do? Decrease the excitation of second machine. Right? Okay. This is only with numericals, and I have given each and every point very, very clearly. Just to go through once again. Okay. And even load condition also, it will be same. Yeah. And other point of the doubt is, I have given one question. After the break, actually. After the break, there was a net issue. Just let me discuss. That is a very important points I want to explain, but it is not come out yesterday exactly. I also not felt I could not able to give the total 100% during that question. So let me explain that question again. Then we will go to the problems. Okay. See. Listen, what is the question I have given? The question is, two alternates connected in parallel. Two alternators connected in parallel. Connected in parallel. And supplying two alternators connected in parallel, supplying to a pure resistive load. Pure resistive load. Pure resistive load. If the excitation of machine 1, the alternator 1, if the excitation of machine 1, the excitation of machine 1 is increased, then power factor of machine 1, then power factor of machine 1 dash and machine 2 dash. Machine 1 dash, machine 2 dash. Alternator supplying for a pure resistive load. Right? And when excitation increases, alternator 1, machine 1 excitation increases, what is its power factor? Only excitation of machine 1 is increased. Then power factor of machine 1 and machine 2. See, this is alternator 1. I want to give some more inputs with this. Alternator 1. Another alternator. Both are connected to a pure resistive load. Pure resistive load. Okay. Yeah. Listen carefully. pure resistive load. This is ZS1 and ZS2. These two alternators, they are connected pure resistive load. See, this is E1 and this is E2, E1, E2. It is delivering the current of IA1 and it is delivering the current of IA2, and both are going to the load. This is I say, I is equal to IA1 plus IA2 to the load. This is the terminal voltage V, terminal voltage V. Okay, yeah. Now coming to, both are operating at what power factor right now? Right now, if E1 is equal to E2, say, E1 is equal to E2, there is no synchronizing current, there is no circulating current. Load want resistive load, na? Load is resistive load. It absorb only active power. The load absorb only active power. Therefore, first machine also supplying only active power. Now second machine also supplying only active power. So load, it is taking, load will take active power. Machine also supplying active power. First machine also supplying active powers. There is no circulating current. Load wants only active power. So both are active power, means only active power is there. First machine operated UPF, second machine also operating at UPF. Initially, both are operating at UPF. Say. Now, excitation of first machine is increased. If you increase the excitation of first machine, field current of excitation increases, E1 increases. E1 increases to some E1 dash. Then there will be a synchronizing current, ISY. And that ISY will be delivered by the first machine. ISY delivered by the first machine, ISY absorbed by the second machine. But when current is there, power also will comes into picture. Na? Power also will comes into picture. Which power? It is reactive power. When excitation changes, it is reactive power. We have verified already. But that reactive power is circulating only in between the machines. It is circulating only between the machines. It is not coming to the load. Why? Load cannot absorb. Load cannot absorb the reactive power. Okay. So it is circulating. When it is circulating means the synchronizing power in the first machine, both active power is there as well as reactive power also there. Second machine also active power is there, reactive power also there. Reactive power is there. Now, will they operate at UPF now? Why students are asking a doubt? Sir, load is resistive load. Therefore, alternator 1, alternator 2, they will operate at UPF. That is their doubt. No. Load power factor UPFA. Load, I am going to draw the phasor diagram. Load power factor UPFA. But machine one power factor is there. Na? Both active power is there, reactive power is there. Then how come it is UPF? No. Second machine also active power is there, reactive power is there. It is not UPF. First machine will operate at lagging power factor, second machine leading. Because I have given one question, standard question. What is that? Statement. Overexcited machine must be demagnetized. First machine we are overexciting. It must be demagnetized. What should be its power factor? Lagging. Second machine underexcited. It must be magnetized. Magnetized means what should be its power factor? Leading. Okay. So though load is resistive, and when excitation of first machine increases, it will operate at lagging power factor, it will operate at leading power factor. Because power factor is not UPF. That you will get more clarity if I draw the phasor diagram. See, to draw the phasor diagram, two ways I can write. See, this is V. For alternator 1, this is V. For alternator 2, I will take on other direction. Voltage V common only. V only same. With respect to local circuit V, that V common. For first machine, I want to draw the phasor diagram right side, second machine left side. And later also, if you want to take same side also, you are going to get the same thing. Let me explain. This is V, na? Yes. What is this? This is IA1. And this is IA2. UPF. Unity power factor. Initially, both are operating at UPF. From there, I am starting. Initially, UPF. Without increasing excitation. And then this is IA-RA, this is IA-XS, IA-XS, this is E, this is E1, E1. Similarly, IA-RA, IA-XS. So this is E2, this is E2, E2, right? So this is the phasor diagram of alternator for UPF right side, left side for machine 2. Okay. Another important observation, dear students, you can find power factor is nothing but angle between V and IA. V and IA. Terminal voltage and the IA1. Terminal voltage and machine current IA1. V and IA1. That is UPF. But angle between E1 and IA. E1 and IA1, some angle is there. What is that angle? Is said to be psi, internal power factor angle. Internal power factor angle. Internal power factor is lagging. Though load is resistive, angle between E1 and IA, it is lagging. Why? Phase difference between E1 and IA coming. Why? Because due to impedance. Winding impedance is there. Due to that winding impedance, phase difference will come. Fine? Yeah. Internal power factor lagging, but load power factor is UPF. Load power factor and angle between V and IA you have to take. V and IA. That is a power factor. So this will be anyhow. Psi will be there. Fine. This is psi. Now, what we are doing, when excitation of machine 1 is increased, say, this is UPF operating. When excitation of machine 1 increase, E1 increases to E1 dash. E1 increases to E1 dash. Now, there is a resultant voltage. Because E1 is greater than, there is a circulating current. This is ESY. ESY will be along the bigger vector. ESY is along the bigger vector. When this is ESY, ISY will be here. ISY always lags. ISY always lags ESY by 90 degrees because winding impedance. Then what is the current? Then current of the first machine is, this is IA1. So in the first machine, both are there. Now IA1 is there, ISY is there. Current machine IA1 is there, ISY is there. Therefore, what is the resultant current? Vector sum of both. So vector sum of both. Therefore, let us take resultant of these two. Resultant of these two. Then what is the current? This is IA1 dash. This is IA1 dash. IA1 dash. Similarly, the resultant current of second machine. Resultant current of second machine, this and this. So that resultant current is equal to this. This is ISY. This is ISY. ISY. Not ISY, sorry. IA2 dash. That will be IA2 dash. IA2 dash is equal to ISY plus resultant of both. Now see, what is the power factor of the first machine? This is phi1 and this is phi2. Phi2. Vectors are rotating counterclockwise direction. Therefore, IA1 dash lags V. Therefore, lagging power factor. Lagging power factor. But what about this IA2 dash? IA2 dash leads V by phi2. Therefore, leading power factor. The first machine operating at lagging power factor, second machine operating at leading power factor. Leading power factor. Right? Yeah. Leading power factor. So further to answer, this much discussion is not required. How to say over-excited machine must be demagnetized, under-excited machine must be magnetized. That is a key point. All these conclusions are verified. Okay, yes. This is one phasor diagram I have taken right side, left side. Na? But some students are asking, no sir, I want to take both are in same side. Okay, you take it. Let me draw. If you want to take in the same direction, how it is going to be? See. This is V now. This is V. This is V. Terminal voltage. Okay. And IA1. Machine current IA1 is equal to, this is IA1 is equal to IA2. Both are same. IA1 is equal to IA2. Currents are equal. Be common. IA1 and IA2 both are in phase. Both are initially operating at UPF. UPF. Okay. Yes. Now IA-RA. This is IA-RA. IA1 RA1. This is IAXES. Okay. IAXES. This is E1. E1 that is also equal to E2. And what was happened? Two phasors are overlapped. And initially both are same rating machine. Both currents are equal and they are overlapped. E1, E2 both are one over other. Phasor diagram one, phasor diagrams both are one over other. Yeah. This is UPF. When excitation is increased, say, if I increase excitation of this machine, so this is E1 dash. E1 is increased. Then ESY will be ESY. This will be ESY. ESY is equal to what? E1 minus E2. That is E1 dash minus E2. That will be along this phasor. Okay, this is resultant. Now, where will be ISY? This will be ISY. ISY lags this ESY by 90 degrees. This is ISY. ISY. ISY with respect to machine 1. Machine 1. The machine 1 is delivering. Current is positive for that. ISY. But second machine, how to take? It is taking. Taking means you have to take ISY. Direction is in opposite direction. This is ISY. ISY with respect to machine 2. Machine 2. Because earlier I have taken voltages reverse, therefore current I didn't change. But now when you are taking voltages same, then current has to be taken reverse. Anyone, either voltages or currents. First one I have taken voltages reverse. But here current we need to change. Then what will be the resultant current? Tell me. For first machine, IA1 and ISY. Resultant of that. What is that resultant? This will be the resultant. This is resultant. So this is the current IA1 dash. This is IA1 dash. Similarly, for second machine resultant of ISY and IA1. IA1. This is IA2 dash. IA2 dash. Now see, this is phi1 dash and this is phi2 dash. Phi2 dash. See, when phasors are rotating counterclockwise, IA1 dash lags. IA1 dash lags V by phi1. Therefore, what is its power factor? Lagging power factor. Lagging power factor. Similarly, IA2 dash lags V. Sorry, not lags, leads. IA2 leads, na? Yes, IA2 leads V by phi2 dash. Therefore, what is its power factor? Leading power factor. Okay. So, whenever you are drawing the phasor diagram, you can draw either E1, E2, you can take same direction, does not matter. But at that time, current direction, ISY is coming now for machine 1, machine 2, you have to reverse. Everywhere, you will get the same answers. Okay? Yeah. Fine. Now I will ask a question for you. This is clear, na? Yes. Now one question for you is, listen. Instead of resistive load, if I am taking some 0.8 lagging load, say 0.8 lagging load, then what is going to be happen? Instead of resistive load, same machine, instead of resistive load, if it is supplying for a 0.8 lagging load, 0.8 lagging load, generalization. Now questions are going to be very simple if you have the concept, this concept, very simple. Now I am using RL load, dear students, RL load. RL load. RL load. ZS1, ZS2. E1. For this, no phasor diagram is required. This is RL load. See, this is resistance RL and XL, reactance XL. Its power factor is equal to 0.8 lagging power factor load. 0.8 lagging power factor. 0.8 lagging power factor load, say. Now, both machines are operating at, this is IA1, this is IA2. So, machine is supplying I is equal to IA1 plus IA2. Of course, it is vector sum. Right now, question for you is, Right now, machine 1 is operating at 0.8 lagging power factor. Okay. Machine 2 also operating at 0.8 lagging power factor because load is 0.8 lagging power factor. Now, my question is, if excitation of initially both are operating at UPF, initially both are operating at lagging power factor, both are operating at 0.8 lagging power factor. If excitation is increased, if excitation of machine 1 is increased, then what is the power factor of machine 1? Dash, and power factor of machine 2 is dash. Power factor of machine 1 and power factor of machine are still more clarity. Excitation increases, power factor of machine 1 and machine 2 respectively A bit, 0.8 lagging, B bit, 0.8 lagging, 0.8 lagging, B bit, 0.6 lagging, 0.9 lagging, C bit, 0.6, this is 0.9 lagging, 0.6 lagging, okay, and D bit, 0.9 lagging, or it is both UPF, say, or this is UPF. Tell me, what is your answer? Or both are 0.9 lagging? Let me take. What your answer? Tell me. This is the question I wanted to give. Tell me, what is your answer? What is your answer? Very good, very good. Answer is C. Answer is B. Answer is B. Why? Because, dear students, so now it is excitation increases, E1 increases, synchronizing current will comes into picture. Synchronizing current will comes into picture. Synchronizing power ISY, and this is ISY. So in first machine, reactive power is increased. Actually, machine 1, machine 2 supplying both active power and reactive power to the load. Okay, IA1 is there, IA2 is there. Both are supplying active power, reactive power. But when excitation of first machine increases, when excitation of first machine is increases, what is happening? Reactive power for the first machine increases, reactive power of second machine decreases because ISY opposing. This is active reactive power increase. I mean to say, in this machine, KVR is increased. This is I have given. KVR of the second machine, what will happen? Decrease. When KVR decrease, what is power factor? Power factor is proportional to active power. Inversely proportional to KVR, na? Yes. And when KVR of first machine is increased, its power factor is going to be decreased. 0.6 lagging. Of course, how 0.6 lagging ante options are given that you need to select 0.6 lagging. And this will be, power factor is going to be increased because KVR reduced, 0.9 lagging. That will be the answer. That will be the answer. Okay. And okay. Still more excitation increases. What is going to be happen? Still, if you give more excitation, and this will be, it may come to the, still it may come. For example, it may come to the, even later, still keep on increases, large increase in excitation. It may still decreases, it may come to some 0.4 lagging, it may come to UPF also. It may come to UPF also, if still increases. If still increase, what will happen? It may come to 0.8 lagging, and it may come to leading also, 0.2 leading also. How much excitation it is increased, that is based on that. How much excitation is increased. Then when excitation increases, reactive power is keep on increases, then its power factor is keep on decreases, but its power factor, second machine power factor increases, 0.9 lagging, UPF. After UPF, where it will go? Leading side. If numerical problem is given, we can say we'll answer. But based on these options, you need to select. So based on the options, that will be B option for this given option. Right? Yes, that is the type of questions. I hope you have got the idea. Based on the options, you need to select, yes, which is the appropriate answer. Right? Only thing is, reactive power is increasing. Other machine reactive power is decreasing. No? Okay. I have given these things in the table already. It is any type of load, how it will be changes. And one student asked this question. Yes. See, similarly, yeah, before coming to the problem, the last point I would like to say, when resistive load is connected, resistive load, an alternator supplying to a pure resistive load. An alternator supplying to a pure resistive load. Supplying to a pure resistive load. Operating at UPF. Operating at UPF. If the excitation of machine is increased, then its operating power factor. Would be A bit, lagging B bit. A bit lagging, B bit leading, C bit UPF, D bit none. Right? Of course, this question also given none. Okay, this is an alternator. Supplying to a pure resistive load. Let me explain clearly. This is operating at UPF. This is V. This is I. This is IA. I. But of course, I is equal to IA only, na? There is only one path. So machine will absorb only active power. When supplying, it will absorb only active power. Correct? Load is resistive load, absorb only active power. Therefore, machine also will deliver only active power. Right? Yeah. So therefore, machine power factor also UPF always. It will always operate only at UPF. Because in that machine, it is involved that V and IA is the same. This is V. Very common sense is current flowing through the resistance, voltage across the resistance. Both are in same phase, na? Yes. Current flowing through that and V. It is same. Right? Therefore, power factor is always UPF. And even dear students, earlier also have given power factor of first machine is, it is going to 0.6 lagging, it is 0.9 lagging. What is the load power factor? Tell me. Load power factor always same. Dear students, load power factor is same. Load power factor will not change. Unless otherwise, if you change resistance value, excess value, the load power factor value will be, what is that? Phi is equal to tan inverse of XL by RL. This is fixed. Machine inside power factor, inside ante, this V and IA1 power factor changes. V and IA2 angle changes. But V and I is there, a resultant, it will be same. Load power factor same. Even here, load power factor UPFA. Machine power factor also UPF. Because this V and IA always in phase. Why? Because this V and IA also always in phase. Machine operate. Okay? It is absorbing active power, it is delivering active power. Correct? Yes. Now, if you increase excitation, answer for me, if excitation is increased, can you tell me, will it deliver reactive power first of all? Initially, both are active power, load want active power, machine delivering active power, operating at UPF. If I increase excitation of this machine, will it deliver reactive power or not? Tell me. Tell me, will it deliver reactive power? Answer in chat box. No. Yes. Why? Why it will not deliver? Why? Because if it is delivering, say, where is the path for that? There is no path for the reactive power. Load cannot take. Then how can it is deliver? It cannot deliver. That also converted to active power only. It cannot deliver. There is no path for the reactive power. But earlier when two alternators are connected, two alternators, another alternator is providing the path for the reactive power. Second alternator is providing. But here, load cannot provide. Therefore, no reactive power will be involved in this. That's the reason machine operate only at UPF. That's the reason I have given an alternator supplying for single alternator, isolated alternator. This is called what? Isolated. An alternator means it is isolated alternator, single alternator. Dear students, single or isolated alternator. Isolated is single alternator. Single alternator always operate only at load power factor. UPFA, whatever you do, it won't change. Right? UPF only. Power factor of single alternator cannot be controlled. Power factor of single alternator cannot be controlled. Power factor is decided by the type of the load. That's all. With excitation, you cannot control. It is always UPF only. And even if you take the load is some other type of load. If, for example, if I am removing this, if load is connected with the RL load, say, if you connect the load with RL load, if it is having some 0.8 lagging power factor, say 0.8 lagging power factor, and whatever you do, you increase excitation, decrease excitation, it's operated 0.8 lagging. Load power factor. Isolated alternate will always operate only at load power factor. Power factor cannot be changed irrespective of excitation. Isolated alternator will always operate. Only at load power factor. Only at load power factor. Irrespective of excitation. Therefore, power factor of single alternator cannot be controlled. Power factor of single alternator cannot be controlled. No, cannot be controlled. Single alternator, whatever the question is, 0.8 lagging power factor is operating. If increase excitation, its power factor is 0.8 lagging only. Alternator power factor same. Because this V, IA is equal to IA. Actually, angle between V and IA is the power factor. That IA itself IA. Load current is equal to armature current. Power factor same. But earlier two alternates are there, na? This V and IA is different, but V IA1 lags. V and IA2. V and IA2. But here V only one current is there. That current is armature current. Load power factor always same means machine power factor also same. Fine. Yeah. Okay. So I hope I have sent the material. Please go through that clearly and you can understand everything. Now let us do some problems based on this. Problems. I want to continue the problems. Okay. See, take down this problem. Just a minute. Problems are very important. I will give only two problems. That will be enough. Yesterday I have done one problem. Na? Okay, similar problems I want to do. 2 or 3 problems. Problem is question. 2 generators, 2 alternators rated 400 megawatt and 600 megawatt are operating in parallel. The group characteristics of governor or 3% and 4% respectively. From no load to full load. From no load to full load. Okay, yes. The generator operating at no load frequency. The no load frequency is 50 hertz. 50 hertz. If the total load on the machines is 1000 megawatts. Then first question, the set frequency is this question is very, very important. I have given similar question yesterday. The set frequency is second question. Load shared by machine 1. Load shared by machine 1 dash machine 2 dash. Third one, the maximum load the set can supply. Without overloading any machine. Yeah. Without overloading any machine. Okay. The two alternators rated. One is 400, another one is 600. Right? Yeah. Right. Let us take. See, I will take the drooping characteristics. One machine is having 400 megawatt, another is having 600 megawatt. This is 400 megawatt. This is 600 megawatt. One alternator. This is having 3% droop. This is having 4% droop. No load frequency 50 hertz. Simplest method this is. Some textbooks you can find some formula. Okay, why to remember formula? After having some idea, you can do very fastly. And some students raise a doubt here. See, this is 50 hertz no load frequency. 3% drop means what is its frequency? Tell me. 50. In 50, 3% is reduced means how much? 1.5 hertz is reduced. 50 into 0.03, 3%. Okay, 1.5 hertz reduced means what should be its frequency? Its frequency will be, right, 48.5. I am going to rub this. Just again, I will delete this. Just for your idea, I am saying 48.5 hertz. And what is its frequency? Its frequency will be 4% reduced means 2 hertz are reduced. It is going to be 48. Okay, yeah. I'm going to delete this. Just have idea. I don't want to calculate that directly percentages I can take. 3% reduced, I will say. And the students are expressing a doubt, sir, why you have drawn this diagram, this triangle. Dear students, the triangle how I am drawing. Triangle, see, the triangle is, this is no load condition. No load means x-axis is load. Whatever I am drawing, it is load. See, for example, this is zero load. What is the frequency? 50 hertz. Zero load, 50 hertz. But when load is increased to some 100 megawatts, say 100 megawatt means its frequency decreasing. Na? Yes, its frequency will be come down. It will come to here. Frequency come down. This is one point. As x-axis increases, y-axis is decreasing. And again, if you increase another 200 megawatt means its frequency will be still decrease. This is the frequency. Similarly, still increase 300 megawatts, say its frequency will decrease. Its frequency will decrease to here. And still again increase 400 megawatt. Okay, 400, 600 like this, 400 megawatt. Its frequency will be still decrease. Again increase 500. Its speed will be still again it is decreased frequency, and increase 600 megawatt. When it is 600, say, when it is increased to 600 megawatt, now the frequency is come down to here. What is its frequency now? Its frequency is 48 hertz. No load, when load is 0, 50 hertz frequency. Dear students, when load is 0, 50 hertz frequency, but as load increases, frequency decreases. Where it is 48 hertz. Now, if you join all these things, what is going to be happen? It will be like this. It is like this. This is what I am drawing here. Okay, this is a triangle for this 600 megawatt machine. Of course, the size is here. I have drawn little bigger. The space is there, not there. That's the reason I am writing. Okay, yeah. This is the way. And no load condition frequency 50 hertz, but when load is increased, it has fall down to 48 hertz. Okay. Second machine I am writing left side. If you draw right side, both will overlap. Don't think it is not minus 400 volts. No, magnitude only important. For that also it will be decreasing. For that also second machine is decreasing. Left side I have taken. Okay. Yeah. I don't want to take this is 48 hertz. All these things are not required. What is important thing? See. Is full load frequency how much? Its full load frequency is 48.5 hertz. Its full load frequency 48. It is full load frequency 48. This is operating at 47. Its full load condition initially both are separately connected. Say is operating here, it is operating here. But when both are connected in parallel, we don't know. Both may be operated full load or some may be different load condition. But both should operate at common frequency. That's the reason what we will do. I will take a line here. Let us make a line. Frequency should be common. Both. For both machines, frequency should be common. This is the F. This is going to be F now? Yes. This is the F I will find. Okay, common frequency. For that, the machine may be, this may be operating at P1, this may be sharing the load P2. Right? Yes. So, how much it is reducing means this is decreasing 3%. Let me take in the percentage, very simple. And this is decreased by X percentage. That X I need to find out. And both are reduced X. X percentage and they are operating at common frequency. No, set frequency is common. That's the reason I am taking common. Y-axis is frequency, X-axis is load. These are the turbine characteristics. And this is operating at what? How much it is reduced? 5%. It has reduced 5%. Okay. Now take the triangle symmetry. See, this is point O. For clarity, I am giving procedure. But after getting some idea, no procedure, nothing. Directly, you can draw that base by base is equal to height by height. This is O, say A, B, say this is C, this is point D, this is point E, this is point F, this is point G. Right? Yeah. Important thing here is from right angle symmetrical triangle is our symmetrical triangle means both are having same hypotenuse. OAB and OCD having same hypotenuse. Symmetrical right angle triangle. In symmetrical right angle triangle, what is that? Ratios of the base is equal to ratios of the height. Base by base is equal to height by height. So, see, in symmetrical right angle triangle, I want to take what is that? OAB and OCD. Ratios of the base is equal to ratios of the height. Ratios of base is equal to ratios of height. Ratios of height. I mean to say, base is equal to AB by CD. AB, correct? Base. This is AB by CD. AB by CD is equal to OB by OD. AB by CD is equal to OB by OD. AB by CD is equal to OB by OD. Now what is AB? AB is equal to 400. CD is equal to how much? P1. That is equal to what is OB? 3%. And what is OD? X. Then P1 is equal to how much? 400 by 3 into X. 400 by 3 into X. Okay. 400 by 3 means how much it will be? Some 1.333. 133.33 X. Let us take this is equation 1. Equation 1. Similarly, next symmetrical right angle triangle. One is over. From symmetrical right angle triangle. From symmetrical right angle triangle. What is that? OBD. These are the another for second machine. ODE and OFG. Correct. ODE. This is one symmetrical triangle. OFG. ODE and OFG. Okay. Base by base is equal to what? DE by FG. DE by FG is equal to OD by OF. OD by OF. Okay. Yeah. But what is DE? DE is equal to P2 by FG 600. That is equal to OD. OD is X percentage and OF is equal to 5%. Then what is that P2? P2 is equal to 600 by 5 into X. 600 by 5 into X is equal to how much? 150X. 600 by 5. 150 into X. Correct? 150, yeah? 600 by 5. How much it is? Yeah. 600 by, is it? No, sorry. I'm sorry. This will be 4, na? Yeah. This is 4. Yes, students, please correct it. This is 4%. 4%. So this will be 4. This will be 4. Yeah, this is 4. That is 150X. Correct. This is 2. Now, but P1 plus P2, how much? Already we know one equation. P1 plus P2 is equal to already given. How much? It is 1000 megawatt. 1000 megawatt. Okay. Yeah. Let me go to the next page. This is equation 3. Therefore, by solving these equations, P1 plus P2. P1 plus P2 is equal to, it is 1000. P1 plus P2 is equal to 1000. So P1 is equal to what? 133.33x. P2 is equal to how much? 150x. 150x. So that is equal to 1000. Then what is the x value? Then x is equal to 3.529 as per my calculation. Okay. 3.529. Then first question, set frequency how much? Set frequency is equal to, set frequency, dear students, set frequency, it is 50 hertz now, first 50 hertz. Now it has reduced by X percentage, it is reduced. X percentage it is reduced. X percentage reduced means 50 minus X percent, that is the frequency, rated frequency. Okay. This is itself frequency. Whatever we are calculating, that is going to be F, frequency. That will be set frequency. This we have to find. That is equal to 50 minus X percentage. That is itself set frequency. So therefore, yeah, coming to here, see. 50 minus X percentage of 50. X percentage. X is drop, yes. So 50 minus 3.529 divided by 100 into 50. That frequency is equal to how much? 48.23 hertz. That is the answer. Set frequency is 48.23 hertz. Okay. Yeah. Now, second question, load shared by machine 1. Load shared by machine 1 is equal to, that is P1. P1 is equal to how much? P1 is equal to 133.33x. That is equal to 133.33. X we are calculated now 3.529. It is equal to how much? 470 megawatt. 470 megawatt. Okay. Similarly, P2 is equal to how much? 150x. 150 into x, 3.529. That is nearly 530 megawatts. Okay, 530 megawatts. Last question is that is another type of question. I am including all 4 questions simultaneously. Okay. Next question, what is that? The third question is the maximum load the set can supply without overloading any machine. Without overloading any machine is given. Any machine is dash, no? Yes. But now, is there any machine, one machine is overloading or not? Yes. Which machine is overloading? Tell me. This machine is overloading. First machine is overloading. In the above problem, machine 1 is overloading. So, machine 1 is overloading actually. Overloading with 1000 megawatts. If 1000 megawatts is there, it will be overloading. It is overloading, na? Yes. Actual load is how much? 400. Actual load is 400. Its full load is 400 megawatts. But it is how much? But it is 470. Overloading 470 megawatt. Then, without overloading any machine, no, machine 1 and machine 2 must be within the limit. It can take full load, okay. And at the same time, the maximum load, how much they can take. See, this is the question. Very important one. For that, also direct step, same thing only. First time when you are doing, it will take time here. But after getting, okay, idea, this much procedure, no steps for procedure, directly, base by base is equal to height by height. Comes practice very quickly. So this is 400, this is 600 megawatt now, 600 megawatt, 600 megawatt, 50 hertz, okay. 3%, this is 4%. This type of problems, how to do? First machine is overloading. Na? How much load? It should not be overload. But how much load it has to take? At least it has to take its full load. Because set load must be maximum, means without overloading, alternator 1 has to take its full load. That's the reason what we will do. Its set frequency will be taken as machine 1 frequency. Set frequency will be taken. Other machine will operate here. Here. I mean to say, so let me write. Yeah, machine 1 is overloading with a total load of, for a total load of 1000 megawatts. Therefore, the net load has to be reduced. Under this case, at this case, the rated frequency of machine 1, is to be taken as set frequency. This is the main point. The rated frequency of machine 1 is to be taken as set frequency. And machine 1, that is therefore machine 1 operated full load. Machine 1 operated full load. That is idea. Machine 1 has to operate at full load. The other machine definitely underloaded. That we cannot do. Let it be underload, but it should not be overload. That is the question. Yes. So that's the reason what we are doing. We are operating set frequency of the first machine, set frequency, full load frequency of first machine, and second machine also has to operate with the same frequency. Same frequency. Yeah. At that time, this is 3%. And this should be, of course, 5%. Not 5%, 4%. 4%. Again, triangle symmetry. Now you can go for with the triangle symmetry. What will happen? P2. Now first machine power is 400. Second machine power is P2. That we need to find. Yeah. From the right angle triangle, P2 by 600. I can take symmetrical right angle triangle is then this and this symmetrical right angle triangle for second machine, this and this. So P2 by 600 is equal to how much? 3 by 4. 3 by 4. Then what is P2? P2 is equal to 600 into 3 by 4. 3 by 4. That is equal to how much? 450. 450 megawatts. 450 megawatts. Then the total load, the set can supply without overloading any machine, is equal to P1 plus P2, but P1 how much it has to take? 400 full load, and P2 will be taken as 450. That is equal to 950 megawatts. 950 megawatts you have to keep. Okay. 950. Now instead of taking 1000, if you take 950, no machine will be overload. That is the maximum. 950 is the maximum. 950 is the maximum. Now if you take 960, definitely first machine is going to be overload. You check it. Again, same procedure you do. More than 950. 960 you take, it is going to be overload. Maximum how much? 950 is only the maximum load the set can supply without overloading any machine. Okay, this is the procedure. Right? Yeah. Now, this is one type of question, but here what I have taken, dear students, what I have taken in this question, no load frequency common is given. No load frequency is given commonly. Right. But some questions, full load frequency common. No load frequencies may be different. No load frequencies may be different. Then how to solve that question? How to solve? Let me give one question. Okay. The question is, two alternators that is machine 1. Machine 1 is 80 kilowatts with a 3% regulation. 3% regulation. Machine 2, it is also 80 kilowatts with a 4% regulation. 4% regulation. Okay, full load frequency is same. Full load frequency of both the machines same. Of both the machines are same. Full load frequency of both machines is same. Both machines is same. Then P1 is equal to, then load shared by machine 1 is equal to how much? Machine 2 how much? Then load shared by machine 1 is equal to how much? Machine 2 is equal to how much? How much? Machine 1 how much? Machine 2 how much? See, for first machine, under this condition, how to take your diagram like this. Full load frequency same. Full load frequencies are common. Okay. But their no load frequencies are different. See, this is also 800 megawatt. This is also 800 megawatt. 800 megawatt. This is having 3%. This is having 4%. 4%. But their full load frequency same. Dear student, full load frequency same. No load frequencies are different. No load frequencies are different. Then what is the load shared by machine 1 and machine 2? Machine 1 and machine 2. Now, listen. So under this, what to do? You take a common frequency. No? Load is how much? Total load has to be given. Na? Yes, yes. Total load. Yeah, total load I have not given. Total load is 1200. Sorry, please you write down. Total load. Total load is 1200 kilowatt. That must be given. 1200 kilowatt. When total load is 1200 kilowatt, okay, these are 800. But total load is 1200 kilowatts is kept up. What is their load? So for that, what I will do? Simply you take one line, common frequency. Set frequency is same, na? Yes. Set frequency, it is operating here. This is my F, set frequency. Set frequency. You just draw a line, horizontal line, because x-axis is common. Now, I will take x from here onwards. This is the important thing. You have to take x will be from here onwards. Earlier, no load frequency same, na? Earlier, no load frequency same. But now it is full load frequency same means what you have to do is full load frequency will be taken as a reference. That's the reason x will be taken. This is x. X will be taken from here. From full load frequency onwards, x. X I will take from bottom onwards. Earlier, you see, earlier how I have taken? Earlier I have taken no load frequency common. That's the reason from no load to common x I am taking. No load will be measured from, x will be measured from no load. Reference is taken no load frequency. That is a common. But now full load frequency is reference, now full load frequency same. Therefore, you count from x from here onwards. X from bottom. Okay. Earlier no load same. Okay. Yeah. Then this is x means what is this value? Tell me. This will be 3 minus x, na? 3 minus x. That is 3 minus x. Then what will be this value? This will be 4 minus x. That must be 4 minus x up to here. 4 minus x. Okay. Take this is P1. This is P1. This is P2. Now tell me equation directly. From the symmetrical right angle triangle. From symmetrical right angle triangle for first machine. Symmetrical right angle triangle. I don't want to put B1 nothing. P1 by, okay, in this right angle triangle, P1 by 800 is equal to 3 minus x by x. Sorry, 3 minus x by total 3. This is 3. Height 3 minus x plus x is equal to 3. Na? 3 I have to take. So P1 by 800 is equal to P1 related to here 3 minus x. 3 minus x divided by 3. Therefore, P1 is equal to how much? 800 by 3 into 3 minus x. 3 minus x. Okay, this is equation 1. Equation 1. Similarly, second machine. For second machine, tell me, this is the P2 divided by, sorry, this and this. These are the two right angle triangle. One and this. So for that, base by base is equal to P2 by 800. P2 by 800 is equal to how much? For P2, 4 minus x divided by, okay, 4 minus x divided by 4. Because this total height is 4, no? Total height you have to take. This height, 4. Then P2 is equal to how much? 800 into, that will be 800 divided by 4 into 4 minus x. That is second one. But again, as usual, our P1 plus P2 is equal to how much? 1200. 1200. P1 is equal to 800 by 3 into 3 minus x. Plus this is 800 divided by 4, 4 minus x. That is equal to 1200. Therefore, what is x calculate? X value should be, x value is equal to 0.857. 0.857. 0.857. Okay, yes, 0.857. Then P1. P1 is equal to how much? 800 by 3 into 3 minus x. That is equal to 800 by 3, 3 minus 0.857. That is equal to how much? 571.44. 571.44 kilowatts. That is P1. Similarly, P2 is equal to 800 divided by 4 minus 4 minus x. 0.857. That is equal to how much? It will be 628. 628.58 kilowatts. Okay. I hope you understood now. Yes. Full load frequency common from exit will be taken from full load onwards. No load same means no load to no load onwards. You have to take reference. Okay. And even the material I have given. Full load frequency may be different. Even no load frequency also may be different. That also same procedure. Just to go through that problem I have given. Solved problems I have given. These type of problems in the material I have given. Okay, all varieties of problems are given. Right? Now, next another important type of problems I am going to discuss. These are important problems, and another frequently asking problems are. Yeah, let me give. This completed, no? Yes. This will be the last problem. After that, we will go to the next topic. See, the question is, figure shows speed or frequency, load characteristics of two generators supplying in parallel to a load. Supplying parallel to a load of 2.8 megawatts. 2.8 megawatts. And the characteristics are given here. The characteristics are this is 51.8 and the slope is given, slope 1 Hz for megawatt, 1 Hz for megawatt. And other one is, this is slope 1 Hz for megawatt. That is also slope 1 Hz for megawatt. This is generator G1 and G2. This is generator G1, generator G2, generator G2. Generator G2. This diagram is given. If you want to give ESC examination questions, you can find very frequently 2008, 2008 to 2012, 2014. Every year this question was there. Even GATE 2014 also one question is given. I am going to give that. The single step questions, all these are after having practice. See, this is x1 is given, x2, x1, x2. Okay, this is 51. 51. 51. Okay, and also given the points. This is A, this is B. Okay. C, D. Right. So answer is A bit. After giving this, the figure shows speed load characteristics. This is the figure showing speed load characteristics. A bit. At what frequency the system is operating and what is the load supplied by each machine? At what frequency? At what frequency the system is operating? And what is the load shared by? And what is the load shared by? What is the load shared by each machine? Each machine. This is A bit. Each question is one question. I am adding all the type of varieties of questions in the same problem. If the load is now, if the load is now increased, the load is now increased by 1 megawatt, what will be the frequency? What will be the frequency? What will be the frequency and load sharing? And load sharing. C bit. In part B, which should be the set point? Which should be the set point? Which should be the set point? Which should be the set point of G2, of generator G2, for the system frequency to be? For the system frequency to be? System frequency to be 50 hertz. 50 hertz. What should be the load sharing? What should be the load sharing? Load sharing. No. Okay. Very, very important question. Triple star question. The same question I am adding all the cases. All the cases I am adding. After this, I am going to give a gate question. How simple it will be. First time when you are doing, it may take some time. Yeah. I hope question is clear for you, na? Yes. This is the diagram is given. Total thing diagram is given. I am taking some conventional question. In that everything will be added. This is a previous ESC examination question. Conventional bit. Yeah. See. Okay. Question is clear for you, na? It is given 1 hertz. Slope is given. Earlier it is given drooping percentage, 3% drop, droop, and 4% drooping characteristics. But here drooping only, slope is giving now. Slope is giving. He has given the slope. Now based on that, we need to find. Let us see. This it is also given. It is also given. This is y-axis. This is x-axis. This is y-axis and this is x-axis. It has given x. Y and x plane. Right. See. Yeah. So this is slope. 1 hertz per megawatt. This is also slope. 1 hertz per megawatt. It's operating at this point. X1, X2, no? Yes, X1, X2. This is 51.8 and this is 51 hertz. This is hertz. This is also hertz. Okay. Now let us write our equation. This is y and this is x. Na? Yes. Dear students, important thing is you may be knowing these are the y is equal to minus mx plus c. These characteristics are nothing but slope is given. When slope is given means what we will do is y is equal to minus mx plus c. Because since the slope is negative, since drooping, therefore slope is negative. Therefore slope is negative. Slope is negative. The equation of straight line. Equation of straight line. Not passing through origin. Is not passing through origin. Y is equal to minus mx plus c. Why minus? Because slope is negative. Slope is negative. Okay. But what is y? Y is the frequency. Y is the frequency as given. X is the load, megawatt. X is in megawatts. X is in megawatts. 1 hertz per megawatt is given, na? Yes, X is in megawatt. Y is frequency. Frequency in hertz. Okay. And X is load. Load in megawatts. Megawatts. Okay. And M is the slope. M is the slope. C is y intersect. C is y intersect. C is a y intersect. Okay. Then y is common. Na? This is y. Frequency common. Set frequency. Set frequency, that's f we need to find. This is the f, set frequency. So I am writing for first machine. F is equal to, tell me, f is equal to, and y is equal to mx plus c, na? Minus mx plus c. Y is equal to minus mx plus c. Here y is f. I will write y is f. Y is f minus m. Minus 1. Minus 1. M is slope for first machine minus 1. Of course, on the diagram it is given 1 hertz. Magnitude is given. But you have to take it will be minus 1. Minus. Okay? Yeah. Minus 1 into x. What is x? X is equal to x1. We don't know x1. That is. Plus c how much? 51.8. Y intersect, na? This is y intersect 51.8. Minus 1, slope is minus 1. Negative, it is drooping. Drooping, na? Yes. Drooping. 51.8. And that is also equal to, for second machine also same, na? Frequency same. Set frequency same. Set frequency same. Minus 1 into x2 plus 51. Set frequency same. Set frequency is same. Set frequency to be taken same, na? Yes, I am equating the set frequency. Equate set frequency. Yeah, now, therefore, from this what you will get? From this what we will get? X1 minus x2. X1 minus x2 is equal to how much? 0.8. x1 minus x2 is equal to 0.8. Then what is x1 plus x2 is given. x1 plus x2 is equal to total load 2.8 megawatt. It is given total. Total load is x1 point x2. x1 is the load now? Yes. Then solving these two, you will get, right? These two will get cancelled. So that is equal to 2x1. 2x1 is equal to 3.6. 2x1 is equal to 3.6. Then what is x1? Okay, x1 is equal to 1.8 megawatts. Then what is x2? x2 is equal to 1 megawatt. x2 is equal to 1 megawatt. Okay, yes. Then frequency, set frequency how much? Set frequency f. F is equal to, I will substitute in this relation, from this relation. F is equal to minus 1 into x1 plus 51.8. Therefore, minus 1 into x1 how much? x1 is equal to 1.8 plus 51.8. How much it is? Set frequency, it will be 50 hertz. 50 hertz. This is answer. Okay. Set frequency, this is answer. Set frequency. And these are the answers. These two are answers. And these are also answers. So load shared by machine 1, machine 2 is equal to this much. How much? 1.8 and this. Okay. That is a bit. What is that? That is a bit. A bit. Now B bit, let us do same procedure. But in B bit, what it has given? See, B bit it is given. If the load is now increased by 1 megawatt, if you increase the load by 1 megawatt, what will be the load sharing? The earlier total load how much? 2.8 megawatt, na? Yes. Earlier the total load is 2.8 megawatt, but now it is increased to some 1 megawatt and 3.8. Then what is the load shared by machine? What is the set frequency? What is the load shared by 1? What is the set frequency? Procedure. See. Now I will write the directly equation B bit y is equal to minus mx plus c again. Mx plus c. Now equating the set frequencies by equating the set frequencies yeah, according to that y is equal to minus mx plus c, na? Yes. So what is that? F is equal to minus 1 into x1 plus c how much? 51.8. First equation same, minus 1 into x2 plus 51. Therefore, x1 minus x2 is equal to how much? 0.8. This equation same, 0.8a. But what is x1 plus x2? x1 plus x2 is equal to, x1 plus x2 how much? 3.8. x1 plus x2 is equal to 3.8. Why? Because since that is 2.8 plus 1 megawatt is equal to 3.8 megawatts. 3.8 megawatts. Increase. Now solving these two. So 2x1 is equal to 2x1. 2x1 is equal to how much? 3.8 plus that is equal to 4.6. 4.6. Then what is x1? x1 is equal to 2.3 megawatts. Then what is x2? 1.5 megawatt. This is answer. Okay. Now similarly f1 how much? Set frequency from this. F is equal to minus 1 into x1 plus 51.8 plus 51.8. That is equal to minus 1 into x1 is how much? 2.3 plus 51.8. 51.8. That is equal to how much? 51.8. Value is okay 49.5 hertz. 49.5 hertz. That is the answer. 49.5 hertz. Set frequency. B bit. And C bit. C bit. See what is the C bit? Yeah. Let us complete and we will go for break. And after the break, we are going to start very important topic: parallel operation of alternator with infinite bus bar. Infinite bus bar we are going to see. Okay. If you miss that, and then so you are going to lose. Don't miss that topic. Because some after break, some students are relaxing. Okay. Next part you see. C is question number C. In part B, which should be the set point of G2 for the system frequency to be 50 hertz? What should be the load sharing? In part B, what is the frequency we have got? 49.5. After solving that, our answer 49.5. 49.5. But I want to increase the frequency to be 50 hertz. You want 50 hertz. Then what to do? What to do? Set point of G2. Set point of G2 means G2 prime mover input has to be increased. Set point is nothing but for generator 2. E is the set point. 51 hertz is the set point. No load frequency is called set point. Dear students, no load frequency is called set point. And as load increases, frequency will be decreased. That's how much setting your no load condition? 51. But here 51, and so therefore what should be the set point? And 49.5 hertz is there na? The B bit just now we are calculated, dear students. Just now we are calculated. What is the frequency? 49.5 hertz we have got. But now it has to increase to 50. It has to increase to 50 means what to do? Generator G2 prime mover input has to be increased. When frequency to increase means you have to increase either generator 1 or prime mover input of generator 2 or both also. But in the data, what is giving? Generator 2 has to be increased. He is asking to increase the generator 2. Okay? Yes. Let us do this. I hope question is clear for you. See, as in part, now we are doing C bit. As in part, the set frequency is 49.5 hertz. 49.5 hertz. Now to increase the speed, 49.5 hertz. To increase the speed, to increase the frequency to 50 hertz. To increase the frequency to 50 hertz, right? The prime mover input has to be the prime mover input of machine 1 can be increased, or machine 2 can be increased, or both can be increased, But in the data given, generator G2, but machine 2, it is the data given, generator 2 or machine 2 power factor, machine 2, prime mover input of machine 2 has to be increased. Prime mover input of machine 2 has to be increased. Okay? Yes. And when prime mover input of machine 2 is increased, see what is going to be happen here. It is like this. Yeah. Slope is same. Slope 1 megahertz only, 1 hertz per megawatt. 1 hertz per megawatt. This also slope is equal to 1 meter. This is same. Slope is not going to be changed. Turbine characteristics same. 51.8. This is 51. 51. 51. Okay. When prime mover input of machine 2 is increases, this is G1 and G2 na. When prime mover input of G2 increases, its characteristic shifted upwards. When prime mover input of machine 2 is increased, then its characteristics will be shifted upwards. They will be shifted upwards. These characters are going to be like this. They will shift upwards. Same only, slope same. Again, slope is not going to be changed. Slope will be same only. 1 hertz per megawatt. Slope same, but characters are shifted upwards. It is coming to here. Then this is the set point E. That E dash you have to find. Earlier it was E, na? Yes. Now E dash is how much that we need to find. E dash. Okay. Yes. Set frequency. What is the set frequency? Set frequency will be 50 hertz. Set frequency is the 50 hertz. This is X1 say. Now this is X2. This is X2. From here to here. That is X2. This is X1. But what is this frequency? This is 51. Okay. This is the frequency. This frequency how much? 50 hertz. That is F. This is our F, 50 hertz. F should be equal to 50 hertz. Okay. Now write the equation. Equation is y is equal to minus mx plus c. But what is F? Your frequency will be, F is equal to first machine same, minus 1 into x1 plus C, 51.8, it is same. That is equal to, again, minus 1 into x2 plus E. E, I don't know. Now E will be changes. That E dash you have to find. E dash we don't know. How to find? F is equal to 50 as given. We want 50 Hz frequency. We want what is should be the frequency? 50 Hz frequency we want. Therefore, 50 I will substitute. Minus 1 into x1 how much? X1 we don't know. X1 that is plus 51.8 is equal to minus 1 into x2 plus E dash. Therefore, by solving this, first I will only substitute in this. Okay, that is equal to 50 is equal to minus 1 into x2 plus E dash. So what is x1? Tell me. From this relation we can calculate from this relation. What is x1? X1 is equal to 50 is equal to 50 is equal to minus 1 into x1 plus 51.8. First equation I am taking. First equation. So what is the answer? X1 is equal to how much? Tell me. From this x1 is equal to 1.8 megawatt. Then what is x2? X2 will be equal to 2 megawatts. X2 is equal to 2 megawatts. Okay. X2 2 megawatts. Now E dash, can you calculate E dash? That E dash can be calculated. F already we know, na? F is equal to, again from this relation. F we know. Yeah. F is equal to what is that? F is equal to minus 1 into x2 plus E dash. That we know again, E dash. Minus 1 into x2, how much? 2 plus E dash. But what is F? F is 50. Therefore, what is E dash? E dash is equal to 52. That is the set point. This is the answer. This is the answer. Therefore, E dash is equal to, that is the answer. E dash is 52 hedges. That is the set point. Therefore, set point is equal to 52.8. Therefore, set point means no load frequency. No load frequency of machine 2. That is E. E is equal to, E dash is equal to how much? 52 hedges. If you adjust, that is 52 hedges. Okay. E dash 52 hedges. Now set frequency will be 50. Set frequency will be 50. Okay. Right. That is your question. Right? Yeah. Okay. We have spent this much time on the problems. Now I will give one gate question you have to do within 1 minute. I will give 1 minute for you only. You have to answer. Gate 2014 examination question for 2 marks. For 2 marks. Directly I am giving. He has given this diagram is given. Diagram is given. The first machine 51.5. Second machine is 51. This is 51. Okay. The slope is 1 hedge per megawatt. Slope. 1 hedge per megawatt. The slope is also 1 hedge per megawatt. 1 hedge per megawatt. Okay. Yes. And this is P1 and P2. P1 and P2. And P1 plus P2 is equal to P1 plus P2 is equal to 2.5 megawatt. 2.5 megawatt. Then what is the set frequency? Then set frequency is dash hedges. Tell me. That is your question. This is only a question. You have to say within 1 minute. What should be the answer? I want to know. Tell me quickly. Tell me quickly. Okay. What is the answer? Answer. 50 hedges. 52 hedges. 50 hedges. Exactly 50. Your answer is correct. The solution, now I know only one step. What is that? Y is equal to minus mx plus c na. And f is same. F is equal to minus 1 into P1. Okay. X is P1. Minus 1 into P1 plus 51.5. That is also equal to minus 1 into P2 plus 51. Therefore, what is P1? That is P1 minus P2 is equal to 0.5. But P1 plus P2, how much? P1 plus P2 is equal to P1 plus P2 is equal to 2.5. Then what is that? 2P1 is equal to 3. Then P1 is equal to how much? 1.5. 1.5. Now in this frequency F is equal to minus 1 into P1 plus 51.5. What is that? Minus 1 into P1 is 1.5 plus 51.5. So what is that answer? 50 hedges. Therefore, this is the answer. Answer is 50 hedges. Okay. What is there? Can't be able to do this is within 1 minute. Yes. But only practice. At the beginning, while we are doing what is this problem Saru is doing is very lengthy problem. Okay. If you do some conventional problems, the subset of the problems, definitely being the student, you have to do some conventional type of problems. It includes all varieties of problems in the same question. I have done so many last 3 bits. No? And this question is it is a part of that we have done. It is a small part of that question. Okay. Yeah, fine. So with this we are completed, and you do practice some more problems. I have given all varieties of problems in the material booklet. I have given book in that all problems, exam solved problems I have given. Please go through that. Different other type of problems also. Because time limitation, I come to do all problems, but these are the problems for examination point of view. Is keep on asking. Okay. Yeah. So now after the break, very important topic I am going to start. That is the parallel operation of alternator with infinite bus bar. And from here onwards, an infinite bus bar, synchronous motor, generator concepts are same. First I will discuss very clearly for generator operation, then motor operation. Not much discussion is required. And this topic is completed. Alternator and bus bar is completed. Say synchronous motor, almost half of the topic will be completed. Okay. So therefore, don't miss that topic. Don't miss the topic after the break. After the break, don't miss the class. Right? So let us take the break. Break for yeah. So what is your doubt? Some of the students are raising their hand. What is? Tell me.
Good evening, sir.
Good evening.
Sir, we are doing parallel operation, no, sir?
Yes.
Hello, sir.
From last few problems, the set frequency is sometimes decreasing, no, sir? Is it advantage or disadvantage? Something.
It is, two alternators set frequency may increase or decrease. It is not connected to the grid, na?
Yes,
They will operate and they will set that frequency. They will operate. If you want to maintain again 50 edges, we have done. What is we have done? Last problem. You have to increase the mechanical power input of one machine.
One of the machine.
If you want, that is question can be given like anything. Okay.
Hello, sir. Hello, sir.
Tell me.
Hello, sir. 2014 GATE was conducted by IIT Kharagpur, and this year also IIT Kharagpur going to be conducted. So in 14, they have give so much importance on the weightage on this synchronous motor. But so can you expect anything from the previous year paper from same institute?
Generally, that will be scenario. See, in particular IIST Kharagpur or wherever it may be, the same faculty will be there, na? Same faculty, those faculty only, mostly they are going to set that paper, because the paper will be given for experts. So if the faculty is interested in synchronous machines, say, you may be given one question more. But we cannot expect all the time same thing. Only what you have to do, practice all varieties of problem. One problem enough. But I am doing some problems in the material example, solved problems I have given. Do that problems enough. For practice, that I am asking. Okay? You don't.
Slide 10.
Not necessary. Yeah. Sorry?
Sir, can you please come on slide 10?
Slide 10. Okay. Yeah. Right. Let us take the break and then come back. Break is for 15 minutes. 15 minutes break. I am reducing the time. 15 minutes break. Come back.
Sir, slide 10.
Okay.
Sir,
Break.
in the question, the data you have given is 80 kilowatt, and in the triangle, it is written as 800 megawatt. So, sir, what is the actual data?
Oh, sorry. Yeah. 800. It is 800, no?
And sir, total load is also 1200 megawatt.
Yeah, it is 800. Please correct 800.
Sir, and the total load?
Total load 1200.
Sir, kilowatt, megawatt, what is?
Kilowatts.
Okay, sir. Sir, slide number 8, sir.
Now, please, others also, you please correct it. It is 800. Okay.
Thank you, sir.
Yeah.
Sir, slide number 8.
Slide number 8. Yeah.
Sir, in the set frequency, why did you reduce the percentage, sir? I didn't understand the percentage section.
Yeah, you can take percentages, or else you can take 3% means 1.5 hertz also if you take. Then Y2 conversion directly I am taking percentage.
Okay, sir.
Even if you take 1.5 hertz also, you will get the same thing.
Oh.
Okay. Yeah.
Okay, sir. Got it.
It's
Sir. Thanks.
easy. No conversion, nothing. Directly you can take.
Thank you, sir. Thanks.
Yes. Yes. Take for 15 minutes. Yes. Yeah. Okay, are you ready? And yeah, it's one correction in that earlier it is in this problem. Please make it 800 kilowatt. I have taken the data 800, but here I missed 10. Okay, please correct this. This one, no? This one. 800 kilowatt. Total load is 1200 kilowatt. Total load is 1200 kilowatt. 1200 kilowatt. Please correct that point. Okay. Yeah. Now, then let us start the next topic. And the most important topic is parallel operation of alternator. Alternator in parallel with infinite bus bar. Alternator in parallel with infinite bus bar. Alternator in parallel with infinite bus bar. Infinite bus bar. Infinite bus bar. Okay. See. Alternator in parallel with infinite bus bar means infinite number of alternates are already connected. Infinite bus bar means what? Infinite number of alternates are connected. We have seen 2 alternates are connected in parallel. Minimum number we have seen. Next case is infinite, maximum number of alternators. Infinite means theoretically infinite. Practically, large number of alternates are connected in parallel. Yeah, let us see. This is the bus bar to which so many alternators are connected. This is alternator number 1. Okay. Like another alternator number 2. Like infinite number of alternates are connected. Infinite number of alternates are connected. Infinite. All these are the alternators. Theoretically, infinite number of alternates are connected. And one more alternator also connected in parallel. This another alternator is also connected in parallel. Is also connected in parallel. Okay, yes. Before connecting, all the conditions has to be satisfied, na? Yes, all the conditions has to be satisfied. Voltage must be same, its frequency must be same, everything will be verified, and then it will be closed. This alternator, and this alternator, this is the transmission line. Transmission line. At the receiving end, loads will be connected. Receiving end loads will be connected. These are the loads. Infinite number of loads will be connected. Loads also. See, this is a load 1, load 1, load 2, up to infinite loads. Loads also, infinite number of loads are connected. These are the loads. Loads. Fine. This is itself a transmission line. All they are connected, na? Yes. These are set. This is transmission line. Transmission line, it will be hundreds of kilometers distance. Transmission lines, 100 kilometers of distance. So infinite number of alternates are already connected, and this alternator also has to be connected in parallel. How? All conditions will be satisfied. Frequency, phase sequence, and everything is verified, and this alternator is also connected. This alternator also connected to the bus bar. So first of all, what is infinite bus bar? Infinite bus bar is nothing but infinite number of alternates are connected to the bus bar. That is infinite. Large number. Infinite means large number of alternates are connected. And it can be defined like this. Infinite bus bar can be defined like this. Infinite bus bar is 1 if a finite amount of power is fed to the bus bar. A finite amount of power is fed to the bus bar or consumed from the bus bar. There will be no change in its voltage and frequency. A finite amount of power is delivered or fed to the bus bar. Fed to the bus bar means some alternates are connected. You are feeding the power to the bus bar means some alternates may be connected or consumed from the bus bar. Some loads may be connected. There will be no change in its terminal voltage and frequency. The voltage and frequency remains constant. So for example, its terminal voltage, say terminal voltage is some 11 kV, and frequency is some 50 hertz, say 50 hertz. That remains constant. They remains constant. They are not going to change. The infinite bus bar is 1 if a finite amount of power is fed to the bus bar and some alternates are connected or consumed from the bus bar. There will be no change in its terminal voltage and frequency. So both terminal voltage and frequency remains constant. And it can also be defined. Infinite bus bar also can be defined like this. Infinite bus bar can be considered as an voltage source, ideal voltage source. It can be considered as an ideal voltage source with zero internal impedance and infinite mechanical rotational inertia. With zero internal impedance means no drop of voltage. But ideal voltage source, no drop, na? Yes, ideal voltage source impedance is 0, no drop of voltage, and the voltage is constant. And infinite mechanical rotational inertia. Infinite rotational inertia means speed is constant. So frequency is constant. But how it is the internal impedance is 0 means, for example, here so many alternates are there. This is ZS, that is in parallel with ZS, that is in parallel with ZS. Like infinite number of alternates are connected in parallel. What is its equivalent impedance? Tell me. What is its equivalent impedance? ZS divided by infinite. That will be 0. The equivalent impedance is said to be 0. When equivalent impedance is 0 means no drop of voltage. So voltage is constant. No drop of speed also. Speed also remains constant. Infinite inertia means speed is constant. Frequency constant. Therefore, an alternator operating on the bus bar. This alternator operating in the bus bar, its terminal voltage remains constant. Frequency remains constant. Even if you increase the excitation of this machine, if you increase excitation of this alternator also, its terminal voltage will not increase. Terminal voltage remains the same. Why? Because these terminals are connected to the bus bar. So common frequency, common voltage. Alternator, if you increase excitation, then the conclusion is an alternator operating at the bus bar, its terminal voltage remains constant, though excitation changes. And its frequency and speed remains constant, though mechanical power input changes. Later, if you increase mechanical power input, it won't change. Its speed will be constant only. Speed will not change. Even increase prime mover input, decrease prime mover input, it will rotate at constant speed only. Speed is not going to be changes because speed same, frequency same. How it is same, that we are going to see. Okay? Yeah. So first let me write infinite bus bar is 1. Infinite bus bar is 1. Infinite bus bar is 1 if a finite amount of power finite amount of power is fed to the bus bar. Power is fed to the bus bar and consumed from the bus bar and consumed from the bus bar. Consumed from the bus bar. There will be no change in its. There will be no change in its. No change in its terminal voltage and frequency. No change in its terminal voltage and frequency. Both terminal voltage and frequency remains constant. Both voltage and frequency. Both voltage and frequency remains constant. Both voltage and frequency remains constant. Remains constant. And also you can define like this. An infinite bus bar can be considered. An infinite bus bar can be considered as a voltage source. Can be considered as an ideal voltage source. Ideal voltage source. Ideal voltage source means that is with zero internal impedance. With zero internal impedance. With zero internal impedance means no drop of voltage. No drop of voltage. No drop of voltage. And infinite rotational mechanical inertia. The infinite inertia means speed constant, speed won't change. Infinite rotational mechanical inertia. That is, speed remains constant. Speed remains constant. No voltage drop or no drop of speed, in other words. No drop of speed. No drop of speed. The both frequency and no drop of speed, no drop of frequency. No drop of frequency. Both voltage and frequencies are extremely constant. Therefore, both voltage and frequency are extremely constant. Are extremely constant. Both are constant. So, an alternator operating on the bus bar, therefore, an alternator operating on the bus bar its terminal voltage remains constant. Its terminal voltage remains constant. Though the excitation changes, and its speed and frequency remains constant, though the prime mover input changes. The alternator operating in the bus bar, speed frequency remains the same. Voltage also remains same. But are there two alternates in parallel? When excitation of any one machine increases, set terminal voltage will increase. A terminal voltage may be decrease. The frequencies also may changes when prime mover input. Two alternators, the frequency, they can settle one particular frequency. But here, alternator will be always operate only at bus bar frequency, grid frequency. So you increase the mechanical power input, decrease it, frequency same. Though you increase excitation, decrease excitation, its terminal voltage remains constant. How it is that we are going to see. Now the question is, Why the frequency is remains constant? Generally, when prime mover input increases, speed has to increase. Na? When speed increases, frequency has to increase. But speed is not going to be changes. Even mechanical power input increases. Let us discuss that. Why? The question is, why the speed and frequency remain constant, though the mechanical power input changes. Though the mechanical power input or prime mover input changes. Prime mover input changes. This is the question. Why? Okay. Why? The speed and frequency remains constant, though the mechanical power input changes. Let us answer for this. Why speed is not changing? Yeah. So alternator earlier. This is our alternator, na? Yes. So for example, this alternator is operating at some 1500 RPM, say. This alternator is operating some 1500 RPM. This is prime mover torque, na? Prime mover torque. Say it is rotating at what speed? Some 1500 RPM, say. Or 3000 RPM. Two pole machine, if you take, it's a 3000 RPM rotating, running. 3000. Now later, if you increase mechanical power input also, its speed is not changed. Speed remains constant. Its voltage constant. How it is? Let us see. Listen, this is alternator connected to the bus bar. Bus bar. When prime mover input changes, this is a prime mover input, na? Yes. Mainly, when you are talking about the speed, we have to talk about one equation. What is that equation? Omega is equal to TPM minus TEM divided by B. Omega is equal to TPM minus TEM by B. You have to talk with this equation. You have to talk with this equation. Yeah. See here, this alternator, initially, what we have done, initially both are equal, say. Isn't here? Initially, the machine will be connected, na? Yes, see, you have to answer for this. So, machine is, before closing the switch, it is rotating at some 1500 RPM, say. It is rotating at 1000 RPM. Prime mover torque is given. It is rotating at 3000 RPM. 3000 RPM before closing the switch. Rotating 3000. But it is said to be operating at no load or full load condition. Open circuit condition. So open circuit condition means how much prime mover input is given? The prime mover input is given only just to meet the losses. Correct? Yes. The prime mover is only just to meet the losses. Mechanical power input is given. Only for rotational losses, na? Yes, friction and windage losses to overcome that. Because no current is there. No current is there. Fine, yes. And now, if it is V is equal to E, say, its terminal voltage is V, the generated voltage also, we are rotating, it is generating the EMF. It is generating the EMF in this, the generated EMF is E, say. The generated EMF E and terminal voltage V. Its terminal voltage is V. Right? Yeah. E is equal to V. No load condition, E is equal to V. Generated voltages are equal and power input is given only to meet the losses. Now, what is the delta here? Delta 0. If you close the switch at this instant, what I mean to say is V is equal to E, na? This is V and E, both are equal. V and E both are equal. This is E, say, that is equal to V before closing the switch. That can be verified with a voltmeter. E and V same. Now, prime mover input is given only to meet the losses. If you close the switch, will be there any power flow takes place? Tell me now. Will be there any power flow takes place? No, no power flow takes place. Because E and V both are in same phase. Both are in same phase. Delta 0, no phase difference. This is said to be even machine is connected. There is no power flow. This is called what? Floating. Machine is floating, just floating. Machine is rotating. It is generating its EMF and E is equal to V, but no power flow takes place. Why? Because potential difference is 0. Potential difference is 0. Machine is said to be floating. Machine is floating. Floating on bus bar. On bus bar. Bus bar. Now, then if alternator has to be loaded, from there onwards, initially power input is given only to meet the losses. Meet the losses at this condition. It is rotating fine, but power input is only to meet the losses. Now, to increase the load on this alternator, what to do? To increase the load on this alternator, increase the mechanical power input, increase the P mechanical. Beyond the losses, earlier losses only, but beyond the losses, when your mechanical power input is given, then the rotor poles will leads. Rotor poles will leads. So this is rotor pole is there, na? Yes, this is north pole and south pole. Rotor poles leads. Then induced EMF leads. When you are pushing with the prime mover, na? When you are pushing with the prime mover, rotor poles leads. When rotor poles leads means EMF also leads like this. See, this is V and E leads. E will come to here. When prime mover input increases, E leads by its phase. E leads. This is delta. Delta increases. Now delta increases. E leads. When E leads means, then this is the potential difference. Potential difference. Now this will be the current. This is the current. IA will comes into picture. IA will comes into picture. When mechanical power input increases, the machine will deliver the current. The machine will deliver the current to the bus bar. Bus bar. Then it will deliver its power. It will deliver the power. And where that power will go? Power will go to the load. Load. As mechanical power input increases, now delta will comes into picture. Due to that vector potential difference, current will comes into picture. Current is coming means current is delivered, power is delivered. Where that power is going? That power is going to the loads. See here, very basic diagram. When I am giving the mechanical power input increased beyond the losses, it will deliver the equivalent electrical power to the bus bar. Delivering equivalent electrical power. And where that power is going? That power is transmitting through the transmission line. It will go to the loads. So this load is taking P1 say, this is P2 say, loads are absorbing that power. Loads are absorbing. But in other words, when you are increasing mechanical power input, it will deliver the power. That power is transmitted through the transmission line they are taking. And in other words, alternator is said to be loaded. Na? Alternator supplying the power means alternator is taking the load. Taking the load. It is loaded. Important point here is load on the alternator. Load on the alternator can be controlled only from prime mover side. Prime mover side, not from load side. Loads are somewhere, dear students. Generating station is somewhere. Loads are hundreds of kilometers. They will be distributed various locations. But your alternator, on your alternator, if you want to load, you want to increase the load means the controlling will be only from input side. If you increase mechanical power input, right, then it will deliver the power output, equivalent power. If you give rated mechanical power input, then it will deliver the rated electrical power. Rated mechanical power means deliver the rated electrical power. So it is taking the rated load. If you give mechanical power input, only half of the rated power. 50% of mechanical power input is given, the power also 50%. Because energy neither created nor destroyed. What is energy? Power into time. How much energy you give, that much energy it will deliver. In other words, how much power you give, mechanical power, that much power it will deliver, that much load it is taking. If you give only 50%, machine is said to be half load condition. If you give rated mechanical power input, it will deliver the rated electrical power to the loads. Therefore, load can be controlled only from input side. Now, can you tell me how to operate this machine under no load condition? Tell me how you can operate. Alternator is already connected. Alternator, all conditions are verified, connected. I want to operate my machine at no load condition. How? No load condition means mechanical power input is given only to meet the losses. To meet the losses, then power output 0. Meet the losses, power output 0. Then it is said to be operating at no load condition. Later onwards, if you increase beyond the losses, then rotor poles will leads. This rotor poles leads, right? Rotor poles leads, north pole and south pole say, right? Rotor poles leads the stator poles. Then delta will increase, vector difference will come, it will deliver power. At a rated mechanical power, it will deliver the rated electrical power. So load can be controlled. Therefore, see, when, yeah, I'm coming to the, again, its original diagram. Due to this, some power flow takes place. Some power flow takes place. When load increases, when prime mover input increases, when prime mover input increases, then the mechanical power input increases. In other words, that is, as P mechanical increases, then P electrical also increases. But P electrical is equal to what? EV by XES sin delta, na? EV by XS sin delta. Therefore, delta increases. Due to this vector potential difference, when delta changing means vector potential difference. Vector potential difference, it will drive the circulating current. Due to this vector potential difference, potential difference between E and V, the current flow takes place, current flow and power flow takes place. Current flow and power flow takes place. Current flow and power flow takes place. If rated mechanical power input is given, say, if rated mechanical power input is given, yeah. See, if rated mechanical power input is given, or I will write in the next page. Next page I am going. If the rated mechanical power input is given, or first no load condition. If the power input is given, if the mechanical power input is given, only to meet the losses, then the machine is said to be, under no load condition, because mechanical power input is equal to losses. P mechanical is equal to losses. Therefore, what is P output? P output, that is P electrical, is equal to 0. No load. That is no load. Right? And if power input is increased beyond the losses, if mechanical power input increased beyond the losses, then the rotor poles leads, induced EMF leads, E leads the V by delta. Okay, yes. Due to this vector potential difference, due to this vector potential difference, power flow and current flow takes place. Vector potential difference, current flow and power flow takes place. Therefore, delta is responsible for current flow. Therefore, delta is responsible for the power flow, Delta is responsible for the power flow. VE, I am not changing any VE. Only when mechanical power input changes, vector difference is coming into picture. Kada? Rotor poles we are pushing. When rotor poles we are pushing means EMF vector also will leads. MMF leads, na? MMF leads means EMF also will leads. So delta is responsible for the power flow. And when rated mechanical power input is given, it will deliver the rated electrical power. If, as the mechanical power input increases, the machine will deliver equivalent electrical power. Machine will deliver equivalent electrical power. Equivalent electrical power to the bus bar. Equivalent electrical power to the bus bar. If the rated mechanical power input is given, right? Yes. If the rated mechanical power input is given, then it will deliver rated electrical power to the bus bar. It means the alternator, it will take rated load. Therefore, the load can be controlled. Therefore, the load on the alternator can be controlled only from prime mover side. Not from load side. Loads are somewhere. Only from prime mover side. Load can be controlled only from prime mover side. Therefore, as P mechanical increases, then P electrical increase, that you cannot stop. Correct? Huh? Energy neither created nor destroyed. You are increasing mechanical power. It will convert electrical power. It will deliver. That is, as TPM, we are increasing prime mover torque. Na? Yes, mechanical power increases means as prime mover torque increases and electromagnetic torque also increases. But in which direction increases, dear students? Opposite direction. When prime mover input increases, electromagnetic torque also increases in opposite direction. Fine? Yes. Opposite direction it will increases. Because it is supplying the load, na? Yes. So, this alternator, as you are increasing prime mover torque, if you increase, as prime mover torque is increased means TPM increases. At the same time, TEM also increases in which direction? Generator means opposite direction. This we have seen already. TPM, because P is going, na, electrical power is going. TPM increases. Electromagnetic torque increases in opposite direction. Opposite. Right? But what is the prime mover torque? We are giving mechanical power here. P mechanical P mechanical power is given. And when P mechanical is given means TPM is equal to P mechanical is equal to TPM into omega. P mechanical is equal to TPM into omega, but P electrical is equal to TEM into omega. TM into omega. Correct? Power is equal to torque into omega. So definitely, when mechanical power input increases, torque increases. Na? Yes, torque increases. Torque increases. Mechanical power increases, electrical power will increase. TPM increases, TM also increases. Which direction? Opposite direction. Opposite direction. The prime mover increases, it is automatically load is falling. Na? Load falls. Therefore, then what about omega? Omega is equal to, therefore omega is equal to TPM minus TEM divided by B. So therefore, as TPM increases, TM also increases. Then what is this? That is constant. Omega is constant. But omega is equal to what? 2 pi n by 60. That is constant means then n also constant. When n is constant, frequency will be constant. Frequency constant. Frequency constant. Okay. So load, even if you increase prime mover input, speed will be constant. Right? Now to say only in single word, general common sense you apply. Dear student, listen. When applying common sense means when I am increasing mechanical power input, automatically it will take the load. Because infinite loads are there, na? An alternator, infinite loads are readily connected. Dear students, loads on the alternators are readily. All infinite alternators are connected, infinite loads are connected. But you are giving your mechanical power, it is converting electrical power. It is transmitted to the load. Which load it is taking, we don't know. But our alternator is supplying the power. In other words, it is taking the load. It is taking the load. So when prime mover input increases, automatically load also increases on the alternator. And as TPM increases, TM also increases. That you cannot stop because loads are readily connected. TPM increases, electromagnetic torque, because load on the machine increases, electromagnetic torque increases, speed remains constant, frequency remains constant. Right? Yes, this is the reason. It's simple to say, prime mover input increases, load also increases. If mechanical torque increases, electromagnetic torque increases. Yeah. Now, yes. See, here active power flow is only one direction. Active power flow always, it will be given mechanical power, it is delivered to the bus bar. Active power flow same. But reactive power flow is in either direction. The reactive power flow may be either direction. Q is there, na? It can be either direction. Active power flow only one direction, from machine to bus bar. Active power flow will be in either direction. But that active power is depends on what? It is depends on the E. This is V, say terminal voltage, this is V. Okay, this is V. What is this? This is E. E. Generated EMF is there, na? It is depends upon E. Reactive power is depends upon E. When you are increasing excitation, field current say, then E also changes. Right? If you are changing field current, E changes. When E changes, Q also will changes. Q also will change. E changes, this changes, Q will change. Right? But Q, if it is delivering, say, Q is delivering means that Q is said to be, it is positive. Q is said to be, this is positive, it is delivering. If it is absorbing, say, it is said to be negative. Negative. So this is said to be delivering. That is nothing but delivering. And Q negative means it will be absorbed. Absorb. But it is absorbing and delivering is depends upon what? Excitation. Excitation. We know that relation. Q is equal to what? Q is equal to V by XES, Q is equal to V by XES into E cos delta minus V. Do you remember this relation? Q is equal to V by XES, E cos delta minus V. But in this V constant, na? In this V is constant, V constant, XS constant, E also constant. Then Q depends upon what? E cos delta minus V. If E cos delta greater than V, Q is positive. Q positive, deliver. If E cos delta less than V, say, what is that? Q is negative. Q is negative means it is absorbed. Negative direction. The absorbing is negative. Generator being the generator, it has to deliver the reactive power. It has to deliver the reactive power. Positive. But instead of that, it is absorbing, say, then it is negative. If E cos delta is equal to V, then Q is equal to 0. Neither deliver nor absorb. So Q is depends upon the excitation. E depends on the excitation. Therefore, based on the excitation, three modes of operation. One is under excitation, over excitation, normal excitation. Let me write. Reactive power flow depends on the excitation. Active power flow is depends on the prime mover input. Yeah. Okay. Active power flow is depends on the active power flow. Active power flow is always from machine to bus bar. From machine to bus bar. But reactive power flow may be, reactive power flow may be either direction. It may deliver or absorb, either direction. And reactive power flow is depends on the excitation. Reactive power flow is depends on the excitation. It depends on excitation. Based on the excitation, three modes of operation. Number one, over excitation. That is E cos delta greater than V. Over excitation, E cos delta greater than V. Second one, under excitation. That is E cos delta less than V. Under excitation, E cos delta less than V. Third one is normal excitation. That is E cos delta is equal to V. Yeah. Now let us see what is over excitation, under excitation, normal excitation. First, I will write the conclusions, and that we are going to realize. First, I will do the highlight. I will write over excitation, under excitation separately. Okay. You have taken up to here? Yes. Over excitation. Let us see one by one. Over excitation, first one, over excitation. See, over excitation. That is E cos delta greater than V. E cos delta is greater than V. Then what is that? Q is positive. We know Q is equal to V by XCS, E cos delta minus V. E cos delta minus V. E cos delta minus V. So, E cos delta Q is positive. When Q is positive means, therefore the machine delivered the reactive power. Therefore the machine delivered the reactive power. Delivered the reactive power and operated. Delivered the reactive power and operated lagging power factor. How lagging power factor? That we are going to see. Operated lagging power factor. Armature reaction is demagnetization. Demagnetization. Why? Because overexcited machine must be demagnetized during parallel operation. It has to demagnetize. Then only your voltage will be constant. When excitation increases also, terminal voltage is not increasing. Why? It will demagnetize. We are going to see that clearly. This is demagnetization. Second one, under excitation. Under excitation. Under excitation, it is E cos delta less than V. E cos delta less than V means Q is negative. Q is negative. When Q is negative means the machine absorb the reactive power. The machine absorb the reactive power. Reactive power and operated leading power factor. Leading. Opposite to motor. Motor under excited lagging. Over excited motor leading. But alternate reverse. Reverse. Over excitation lagging. Under excited generator leading. Motor is going to be lagging. Armature reaction is magnetization. Magnetization. Armature reaction, magnetization. And third one, normal excitation. Normal excitation. That is E cos delta is equal to V. E cos delta is equal to V. Then what is Q? Q is equal to 0. Normal excitation. E cos delta is equal to V. Q0. Therefore, Q0 means the machine neither deliver nor absorb. Neither deliver nor absorb the reactive power. Absorb the reactive power. And operated UPF. Armature reaction is only cross magnetization. Armature reaction is cross magnetization. Armature reaction is cross magnetization. Right? That is a normal excitation. So important thing here is when over excitation, machine deliver the reactive power, operated lagging power factor. Armature reaction is demagnetization. Armature reaction, demagnetization. Similarly, for under excitation, machine absorb the reactive power. Operated leading power factor. But armature reaction is magnetization. Normal excitation neither deliver nor absorb. Yeah. Then why this reactive power is coming into picture? Why it is demagnetizing? Why it is magnetizing? What is the role of the reactive power? Let us see. Role of the reactive power. Role of the reactive power. The role of the reactive power is to maintain the air gap flux constant. Role of the reactive power is to maintain the air gap flux constant. Because machine is V by F ratio constant. Na? Since V by F ratio constant, what is the flux? V by F ratio is constant. Therefore, air gap flux constant. Flux constant. Who is maintaining this flux constant? Reactive power is maintaining. So, listen. Reactive power is, role of the reactive power is to maintain the air gap flux constant, is to maintain the air gap flux constant. Air gap flux constant. Air gap flux means phi r. Air gap flux phi r is to maintain the air gap flux constant. So that the terminal voltage is constant. So that the terminal voltage. So the terminal voltage is constant. Who is maintaining the terminal voltage stability? Reactive power. Reactive power will maintain the terminal voltage constant. And when terminal voltage constant, F anyhow constant. V by F ratio constant means flux is constant. All the meanings are same. Here, phi r. Air gap flux means phi r. Na? Phi r is equal to phi m plus or minus phi a. Plus or minus phi a. That should be constant. That should be constant. Phi r is equal to phi m plus or minus phi a. That should be constant. Plus is for magnetization. Minus is for demagnetization. Magnetization. And this phi m is produced by DC excitation. And who is producing this phi a? Phi a is produced by IA. But magnetization, demagnetization is due to, is it IA sin phi component or IA cos phi component? IA sin phi component. This is phi a is demagnetization or magnetization by net flux is depends on the magnetization or demagnetization. That is depends on the active part of the reactive part of the current. See, for example, this is your main field flux phi m. Main field flux phi m. What is this? This is induced EMF E. This is E. Now say this is current, for example, IA. This is psi is nearly equal to phi, say, for example. Of course, some angle is there. Leave it. For easy understanding purpose, I am taking. And this IA can be divided into two components. Na? IA can be divided into two components. What is one component? This is IA cos phi and this is IA sin phi. This is nothing but IA sin phi. IA sin phi. IA sin phi multiplying with VIA sin phi. VIA sin phi. What is that? That is itself a Q. But current, I am talking about in terms of currents. Where current is there, voltage also automatically there. Na? VI sin phi. That is the reactive power, reactive component. This is only creating the demagnetization for lagging power factor. Phi AD. Who is causing? That is by IA sin phi. IA sin phi. If you take leading power factor, it is going to be magnetization. Lagging power factor, it is demagnetization. Therefore, this IFM, this is by field current IFM. Main field current, DC field current, IFM. And this is by armature flux is by what? IA sin phi. This is mainly IA sin phi causing demagnetization or magnetization. IA sin phi means what? VI sin phi. That is itself VI sin phi. That is itself what? Q. That is Q. Q. Therefore, if you change field current, what is going to be happen? Tell me. If you change field current, phi m changes. When phi m changes, phi a has to change to maintain the constant air gap flux. Phi m plus phi a together constant. When phi m changes, phi a changes. When phi a changes, IA sin phi changes. VI sin phi changes. Q changes. Means So once you just change the field current, Q changes. If IF is changed, if field current IFM changes, then Q will be changes. IFM changes, Q will be changed. Therefore, reactive power is controlled with excitation. Therefore, reactive power is depends on the depends on excitation. Reactive power is depends on the excitation. Excitation. Now, how it is maintaining the air gap flux constant, that I want to explain. Mainly, you should know the terminology. What is the meaning of over-excitation? What is the meaning of under-excitation? These terms are important. While you are coming to the objective question, say the terminology. Over-excitation means what? Under-excitation means what? Right? See. This is clear, na? Yeah. Reactive power will come into picture. When field current changes, reactive power also will come into picture. See, our alternator okay. Yes. In the machine, phi r is equal to, what is that? Phi r is equal to phi m. Phi r is equal to phi m plus or minus phi a. In the machine, phi r is equal to phi m plus or minus phi a. That will be constant. That will be constant. Constant. Constant means, say, let us say it is equal to some 10 milliwebers. 10 milliwebers, say, that is constant. Constant. By P by F ratio constant, flux constant. And who is maintaining this? Reactive power is doing that. I would like to explain. See. When machine is over-excited, first normal excitation let me take. The machine is normal excitation. For normal excitation, say field current, this is IFM. IFM is equal to 10 amperes, say. IF is equal to 10 amperes. When 10 amperes means it is producing the 10 milliwebers. Main field flux is producing 10 milliwebers. 10 milliwebers, then what is this phi a? Phi a is equal to 0. Phi a is equal to 0 means Ia also equal to 0. Phi a 0, therefore Ia is equal to 0. Therefore Ia is equal to 0 means, then what is the Q? Reactive power is 0. Reactive power is 0. Okay? For normal excitation means, when machine is operating at normal excitation, the field current given is just sufficient to produce the required air gap flux. The field current only will developing the required air gap flux. We have given main field current, that is itself producing the 10 milliwebers. Then no need of AC reactive power. It neither absorb nor deliver the reactive power. Okay, neither absorb nor deliver. If under excitation, say, for under excitation means the field current IFM. Field current given is some 5 amperes. Field current I have reduced. Normal excitation, this is 5 amperes. 5 amperes means what is this flux? This will be only 5 milliwebers. 5 milliwebers. But total how much? 10 required. The field current given is not sufficient. Under excitation means whatever the field current given, that is not sufficient for the machine. Then what the machine will do? It will absorb the reactive power. From where? From the bus bar. To bus bar, who is giving? Another alternators are there, na? Remaining all alternators delivering active power and also reactive power. Your alternator also can deliver, but your alternator under excited means it will absorb the reactive power. It will absorb the reactive power. So then it is 5 milliwebers. It will absorb the reactive power and causes magnetization. Magnetization. I have given under excitation, armature reaction is magnetization. Machine operated leading power factor, magnetization. So it is drawing the reactive power, and this is aiding with the DC flux, main field flux. Of course, both are stationary. It is aiding to the main field flux and maintaining the 10 milliwebers. Maintaining the 10 milliwebers. Okay, that is constant. So during this case, what will happen? Q will be deliver. Q deliver, not deliver, absorb. Q will absorb. Q absorb here. Q absorb. Machine absorb the reactive power. It is causes magnetization. Magnetization. Similarly, for over-excitation, say, over-excitation, that is main field current given is 15 amperes, say. 15 amperes means you are given more than required. 10 is sufficient, normal excitation, but you are giving more than that. That will create 15 milliwebers, say, proportional to the current. 15 milliwebers means I need only 10 milliwebers. 10 milliwebers. Then what should be the phi A? Phi A must be minus 5 milliwebers. Minus 5 milliwebers means then also reactive power will comes into picture. But this time it will deliver the reactive power and it causes the demagnetization. When over-excited, the current is coming reactive current. It is demagnetizing the armature flux. When demagnetizes, again it is maintaining the air gap flux constant. Minus 5 I have taken a demagnetization. Then Q will be delivered. Q will be delivered. Yeah. So based on your excitation, Q will comes into picture. If it is under-excited, say, if it is under-excited means field current given not sufficient. What it will do? It will absorb the reactive power and it is magnetizing the core. So two fluxes together will maintain the air gap flux constant. And when over-excited means field current is given more than required. More than required means then the machine will deliver the reactive power and it is causes demagnetization. You are giving extra means demagnetize. Then again it will maintain the air gap flux constant. Normal excitation means whatever the field current is given is just sufficient to produce the required air gap flux. Then no need of AC reactive power. AC reactive power is not required because you are giving sufficient flux. No need of that. So therefore, when reactive power is coming into picture, it is magnetizing or demagnetizing such that air gap flux is maintained constant. And when air gap flux is constant means terminal voltage constant, frequency constant, conversely also correct. So reactive power is maintaining the air gap flux constant. Therefore, terminal voltage will be same. I can make general statement, dear students. I am going to write all the things. General statement: an over-excited synchronous machine deliver. Motor also same thing. Motor also we are going to see. When over-excited, that is also deliver. Generator deliver, motor also deliver. There also demagnetization. Motor or generator. Over-excited condition demagnetized. An over-excited synchronous machine, both generator and motor, deliver the reactive power, they causes demagnetization. Under-excited synchronous machine will be magnetized. Over-excited machine is demagnetized to maintain the air gap flux constant. Under-excited machine will be magnetized. Who is doing this magnetization, demagnetization? Reactive power is doing. That's the reason reactive power is called magnetizing power, or you can also call it demagnetizing power also. Demagnetizing power. An alternator. Same way, induction motor. But singly excited machine. This is alternative doubly excited machine. Singly excited machine like induction motor. Induction motor, induction generator. Can you tell me, is it over-excited or under-excited? Over-excited or under-excited? Under-excitation. No excitation. There is no excitation you are giving. That is said to be zero excitation, also under-excitation. Then what they will do? They definitely has to absorb the reactive power to magnetize the core for the production of working flux. It entirely will absorb only always. to produce a required air gap flux. So singly excited machine, all they will be observed only. Even your doubly excited synchronous machine also under excited, it will also observe. But if it is over excited, it will also deliver. Generally, our machines are designed for over excitation. Alternators are generally designed for over excitation because it has to deliver the reactive power. Their operating power factor normally lagging power factor, over excitation. Right? Yeah. So this is the case. Over excited synchronous machine deliver both generator and motor. So reactive power is coming, it is maintaining the required flux. Required flux. If you give sufficient flux means it won't absorb. You give extra, it will deliver. It will give. Generally, you are giving field current, say, now it is delivering, demagnetizing. Therefore, voltage is maintained constant only. V is maintained constant. Sufficient reactive power is there. Now, terminal voltage is constant. So let me write these things. See, the role of the reactive power is to maintain the air gap flux constant. When the machine is under excited, when the machine is under excited means, it means that is the field current given, is not sufficient, to produce the required air gap flux. To produce the required air gap flux. Required air gap flux. Air gap flux. Then the machine will absorb the reactive power. Then the machine will absorb the reactive power. Absorb the reactive power. Absorb the reactive power and causes. Absorb the reactive power and causes magnetization. Magnetization to maintain the constant air gap flux. To maintain the constant air gap flux. Constant air gap flux. Okay. Yes. Next, when the machine is overexcited, that means the field current given when the machine is overexcited, then that is the field current. The field current given is more than required. The field current is given is more than required. Then the machine will absorb will deliver the reactive power. And causes magnetization, not magnetization, demagnetization, overexcited demagnetization. Causes demagnetization to maintain the constant air gap flux. Constant air gap flux. Okay. To maintain the constant air gap flux. Lastly, when the machine is normally excited, that is the field current given is just sufficient to produce the required air gap flux. to produce the required air gap flux. To produce the required air gap flux. Then no need of AC reactive power. Then no need of AC reactive power. No need of AC reactive power. Okay. Then the machine, no need of AC reactive power. Therefore, the machine neither deliver nor absorb the reactive power. Neither deliver nor absorb the reactive power. The machine neither deliver nor absorb the reactive power. Okay. Yes. And general statement is an overexcited synchronous machine. Yes, I'm going to close. 9 o'clock I will close. Okay. Let me complete the statements. An overexcited synchronous machine will deliver the reactive power. Same statements valid for even synchronous motor also. Synchronous motor also same. Overexcited machine. An overexcited synchronous machine. An overexcited synchronous machine will deliver the reactive power. Will deliver the reactive power. Deliver the reactive power. Overexcited synchronous machine means both generator and motor. Let me give both generator and motor. Both generator and motor. An overexcited synchronous machine will deliver the reactive power. Deliver the reactive power. An underexcited synchronous machine. An underexcited synchronous machine, both generator and motor. Both generator and motor will absorb the reactive power. Will absorb the reactive power. Will absorb the reactive power. Similarly, all singly excited machines. All singly excited machines. Like that is induction motor and induction generator. Induction motor and induction generator. All singly excited machines. All singly excited machines are said to be underexcited. Are said to be underexcited. No excitation. Huh? Are said to be underexcited only they are. Underexcited. That is no zero excitation. Zero excitation. No excitation. Underexcited. They always absorb the reactive power. They come compulsory and absorb. They always absorb the reactive power. Absorb the reactive power to magnetize the core. To magnetize the core. Magnetize the core for the production of required air gap flux. For the production of required air gap flux. Required air gap flux. Okay. Yes. Required air gap flux they will absorb. That's the reason synchronizing power, magnetizing power can be called as demagnetizing or that's the reason. That's the reason reactive power is called magnetizing power. Reactive power is called magnetizing power. Magnetizing power. But in synchronous machine, it may be demagnetizing also. But in synchronous machine, the reactive power may be magnetizing power, or demagnetizing power also. Magnetizing power and demagnetizing power also. Demagnetizing power also. Okay. Yeah. Demagnetizing power also. Fine. So today what we have seen, how frequency is constant and how voltage also constant we have seen. How voltage is constant, reactive power will come into picture, it maintains area flux constant, voltage also constant. And we have seen what is infinite bus bar. Okay, how power flow takes place. Delta is responsible for active power flow. Excitation is responsible for the reactive power flow. And tomorrow, next class, tomorrow you are having, I think, tomorrow class is, what is the timings? 2 p.m. onwards, no? Just a minute, I will see and I will tell. Yeah. Class is tomorrow 2 p.m. to 8:30. Tomorrow class is that is on 3rd October 2021 is from 2 p.m. to 8:30 p.m. 8:30 p.m. So tomorrow we are going to see almost synchronous motors will be completed. Synchronous motor 7th chapter will be started. So we are almost coming to the end of our topic. Tomorrow, after tomorrow, next within 2 classes, or we may be complete within 2 classes, or hardly maximum is 2 to 3 classes, that will be enough. Other than tomorrow, it will be Monday, Tuesday, we will come to the close of our topic, right? So tomorrow, don't miss the class. Tomorrow, alternator bus bar, effect of change in excitation, V curves, inverted V curves, how reactive power is controlled, all those things. Once that topic is completed, synchronous motors are almost completed, because topic is same for generator and motor, it is same. Okay, right. Yeah. Now, then any doubts are there? Please raise your hands. Okay, it is 2 to 8. I don't know. Let us see. Okay. 2 to 8 means we will take 2 to 8. No problem. Don't worry. It is 2 to 8. Okay, maybe 2 to 8. Your doubt is to 8 p.m. If it is given 8 p.m., we will see the same time, whatever the time. But he has sent the timetable for me up to 2 to 8. Fine. Yeah, half an hour, this side, that side, that is depends on in our hand. Okay. Now coming to, tell me any doubts are there. I will unmute. Unmute this, please ask.
Hello, good evening, sir.
Hello, good evening.
Sir, here is this role of reactive power, sir. Sir, here you said that when we vary IFM, it is indirectly controlling the reactive power flow. That point alone could explain, sir, that it is varying this IA sin phi, VA sin phi.
See,
here.
who is creating this phi A? IA sin phi.
Yes, sir.
IA will have 2 components again, IA cos phi, IA sin phi. But mainly IA sin phi will control the flux. It is exactly opposing or in phase. Okay, IA sin phi. And this is multiplied with VI sin phi. That is itself a Q. IA sin phi is nothing but reactive component of the.
Yes, sir.
If you change field current, phi m changes definitely. But when phi m changes, resultant total is constant, no, phi r to be constant. When phi m changes, phi a has to change definitely.
Okay, sir.
When phi m changes, phi a has to change. Phi a has to change means IA sin phi has to change. VI sin phi has to change. Q will change.
Sure. And sir, one last thing, sir. In this this point where you explain this, why the speed and frequency remains constant throughout when being changes.
Yes.
So in that you explain that when prime mover torque increases, electromagnetic torque also correspondingly increases.
Opposite direction.
So that means it will settle. That means omega is being constant.
Yes, 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 yes.
So this property of this machine is not exclusive alone to this when it is connected to bus bar, no sir. It is normally in every machine. Then in that case, speed will be constant only, no, sir. When we give like isolated alternator also, if you increase input, then speed will be constant only, no sir.
No. Single alternator, isolated alternator. If you take isolated alternator, you are keeping load constant.
Yes, sir.
Good point. Load constant. When prime mover input increases, input is increases, but load is same.
Yes,
Then
sir.
whatever input you have given, it will accelerate the rotor over speeding. Whereas on single alternator, load is fixed. You are not changing.
Yes,
but on alternator connected to the bus bar, infinite loads are connected. How much power you give, that much power it will take automatically.
Okay, sir.
It will take. All loads are available.
Okay.
If you give half of the prime mover input, say it will take half of the load only, it will take. Which load it is taking, we don't know. Infinite loads are there. Among them, it is taking some load. You give rated power, rated load, it will take. Proportionally, it will take. That's what. Because loads are readily connected. As a isolated alternate, say load is fixed. I am not changing any load side, I am not changing. Only prime mover side, if you change, single alternator increases, its speed will increase, frequency increases. Are there two alternators? Two alternates also, you are connecting common load. I am not touching the load. I am taking only prime mover side. When prime mover side input increases, say load is same, but mechanical power input increases, its speed increases. So in that is the main difference. Two alternates and infinite bus bar. Prime mover input increases in two alternators. If any prime mover input of any one machine increases, set frequency increases.
Yes, sir.
Or vice versa decreases. But here it is not like that. That frequency will be same because infinite number of alternates are there. Na? So how single alternator will change the entire bus bar frequency? No.
All of them must decide the frequency.
Yes. This is single cannot change. Instead of that, see. Instead of that, for example, some 1,000 alternates are there. 1,000 alternators, one you change, nothing will happen. I am talking about only our alternator. One alternator only I am taking. If instead of 1,000 alternators, right? If you increase some 500 alternator prime mover spot increase, then definitely grid frequency increases.
Okay.
That's the reason I have used finite amount of power is fed. If infinite power is fed means, for example, alternates are there. Still you are giving more another alternators also prime mover speed is increased. Definitely grid frequency also increases. But we are talking already infinite alternates are there. Now you are talking about your alternator. So your alternator increase, decrease, nothing will happen. Because compared with infinite, this is alone cannot change anything.
Sir, my doubt is in the production of this electromagnetic torque, sir. In the case of isolated alternator also, if TPM increases, electromagnetic torque will obviously increase because speed is increasing, flux cutting is increasing, so electromagnetic torque also will increase, no, sir. In the isolated case also, TM is increasing. In if you connect it to bus bar also, TM is increasing. Then in both the cases, shouldn't speed.
How much TM increasing? That is the matter. Where is the load? For example, you have connect. See, universe single alternator. This alternator, just a minute. See, the point here is this is alternator. Okay.
Yes, sir.
Then no load condition. How you will operate no load condition?
You will only give the minimum input required.
Minimum input. Isolate alternator say only one alternator is there. This I am connecting to my load. Okay.
Yes, sir.
It will be connected to a load. Like this, it is connected to the load. Fine. Load. Now, no load condition. If you increase mechanical power input, what is going to be happen? Its speed increases or not?
Yes, sir.
Yes. Why? Because it is open circuited. Only one load is there. That is you are open circuited.
Okay, sir.
When increases, prime mover speed increases, speed will increase definitely. Frequency increases. Here, if no load condition means what I will do, mechanical power input is given only to meet the losses.
Yes, sir.
But if you increase beyond these losses, automatically it will deliver the power. Where is the
Yes,
path?
sir.
Loads are infinitely connected already.
Yes, sir.
But here it is, this is only connected. This you are keeping fixed load, say. For example, this is only 10 kilowatts, that is fixed.
Yes, sir.
Then it is input increases, it will definitely overspeed.
And that the
Ah.
amount of this electromagnetic torque will not be in proportion to this prime mover torque.
Exactly. Because load is finite loads, but here loads are infinite loads are there.
Infinite loads. Yes, sir.
Infinite loads are there.
All right, sir. Thank you, sir.
Yes. Okay. Hello?
Sir,
Yeah, tell me.
sir, here in that point only, that isolated alternator.
Yeah.
That isolated alternator. Sir, if you said that that load is fixed, okay? Means if you will increase the load is fixed. Sir, load is fixed. If you will increase the speed will be increased, na? Hello.
Repeat.
Hello.
Yeah, tell me. Your voice is not clear. Repeat.
Okay, actually some problem.
Tell me.
Audible, sir?
Tell me.
So in that point, if we are increasing the speed will be increased, na?
Yes.
Speed. Here that phi r is not constant. That in infinite was we are maintaining V by F ratio constant, but here I think we are not controlling that phi r is constant. Air gap flux.
Where single alternator?
Single length.
That is okay. I'm not talking about phi r. Phi r is depends upon what? That is again magnetization or demagnetization based on that. Because here V may not constant or for example, as load increases, voltage drop takes place. Since V decreases. Then V by F ratio based on that also phi changes. Air gap flux may changes.
Okay.
But infinite bus bar means, for example, single alternator resistive load is there. See, resistive load is connected. If under excited, will it absorb the reactive power? From where it will absorb the reactive power? Resistive load cannot supply.
Okay.
Those terms are not valid single alternator. Now I cannot say it is over excited, deliver the reactive power, operate lagging power, not like that. Single alternator always operate only at load power factor. That's all. Power factor you cannot control.
Yes.
V curves, inverted V curves, you will get only on the bus bar. That you cannot get it. At that time, I will compare single alternator.
Yes.
Behavior is different. Single alternator, it operates only based on the load power factor. For example, resist load is there, say. You increase excitation, whatever you do, its power factor is same.
Yes.
You not change. Okay?
Yes. Okay.
Yeah.
Thank you.
Right. Hello? Hello?
Hello, sir.
Yeah, tell me.
Sir, in page number, yesterday you told one point was that less grouping characteristics will share the more load.
Provided that if both are same equal rating.
Equal rating.
When both machines are having with the same rating, then it is valid.
Okay, sir.
For all the problems, if they are not valid. For example, 100 kilowatt alternator, some 300 kilowatt alternator. Then we cannot compare.
Okay.
Both are same rating,
Okay.
same rating, then they will share the load proportional to their grouping characteristics.
Okay, sir. Can you please again explain the role of the reactive power, sir? I didn't.
No, what the reactive power is doing, it is causing demagnetization or magnetization.
It's in page number 3, that relation, sir, IFM increases, Q increases.
No. So here, who is creating the flux? Two things they are creating. Okay. Phi r is equal to phi m plus phi a. Who is creating this phi m? IFM.
Main field.
Main field current. Phi a created by IA.
Yes, sir.
But IA will have again two components. See here
Yes.
in this diagram. Who is causing demagnetization? IA sin phi causing.
Yes, sir.
IA sin phi only, multiply with V, Vi sin phi. That is itself Q. You can talk in
Okay.
terms of I sin phi means that is itself Q. Reactive power only producing this demagnetization or magnetization. Reactive power, it will produce the flux, you know. Reactive power and reactive current.
How from IA sin phi to VIA sin phi, how we are writing? Like,
No, I am just multiplying. IA sin phi means that also multiplying Vi sin phi. That is itself a Q. My intention is IA sin phi is itself Q. And ultimately, I am coming to the Q is related to IA sin phi.
yes.
Q is itself IA multiply. So IA current is there, voltage is not there. Voltage will be there automatically.
Yes, sir.
Mainly, I would like to explain relate with Q. I wanted to explain. Okay.
Sir, in page number 10, sir.
Page number 10. Okay.
Not in previous one, sir. Like you explained about excitation, E and V angle delta comes.
Where? Alternate bus bar.
Yes, sir.
No, I'm not getting. What? Where is the exact topic?
Like why speed and frequency remains the constant though mechanical input changes.
This one. This one only, no?
Yes, sir.
See,
Yes, sir.
when prime mover input increases, automatically it will deliver the active power to the load.
Yes, sir.
When active power is increases, what will happen? Electromagnetic torque also increases. Which direction? Opposite direction.
Yes, sir.
How much mechanical power is given? Electrical power also same. So TPM increases, TM also increases. That's the reason this is constant. Here that's what I told. P mechanical increases, P electrical. TPM increases, T electromagnetic also increases. Then both increases means
not like EV relation, like delta comes, that one, sir. Like
this one,
yes, sir, that one. I am not getting the diagram in yesterday's class also.
See, when I am increasing prime mover input, my alternator is there. My alternator is there. Okay. Stator poles, rotor poles. You are pushing the rotor with this prime mover. Then rotor poles leads. It may be counterclockwise direction, clockwise direction does not matter. Vectors are rotating. I am taking counterclockwise direction. Say. When prime mover input is increased, it means rotor poles leads. Rotor pole leads.
Okay, sir.
Rotor pole. When rotor poles leads means MMF leads. Then EMF also will leads.
Leads.
E leading. That's what. See here both E and V in phase.
Yes, sir.
But here E is leading. Why? Why? Because I have increased the mechanical power input. When mechanical power input increases, electrical power increases. But electrical power is equal to EV by X sin delta. How electrical power increases? Delta will increase.
Okay, sir.
Delta will increase as PE increases. It means as PE increases, delta also will increase. That delta is responsible for the power flow.
IA, sir. IA current.
IA will increase. That is okay. IA also will come. IA, why it is coming? Vector potential difference.
Okay.
Hello? Delta increases, compulsory IA increases.
Lagging.
Let it be. Maybe lagging or leading does not
means we studied that. We studied that, no, sir. It is perpendicular to vector.
Yeah, perpendicular only. Why perpendicular? This is J into IA axis, na? This is J into IA axis.
Okay, sir.
For J into IA axis, current will be perpendicular. This is J into IA axis.
Okay, now I got it. Thank you.
That will be IA. Okay.
Okay. Thank you, sir.
Okay. Yeah, I'm closing the session. Right. Tomorrow we'll meet.